Hello, everybody, and welcome. Welcome. Hello. Okay, I can hear myself. Looks like the stream is working. Let's get it going. Make our little announcement. Here is where we are live on twitch.tv/Lenser. Graph coloring. Basics of graph theory and coloring. How about that? Let's not forget to add the note of group. And let's get going. I actually remembered to put my phone on vibrate today, so that's a win. Welcome everybody, welcome King Buzz, gang. What's up, King Buzz? How's it going? What's good? Thank you so much for tuning in, King Buzz. What is up with you? I'd say we should just get right into it. Where are we at? This is the directory. Let's go to the docs. Let's look at developers.txt, set up our compile command. LanderXT says, finally, I'm not 30 minutes late. It's true, I am. It's usually the other way around. Not CMake. You don't need CMake to build the docs. Lamau. My brain's a little fried. Normally I don't eat breakfast in the morning. I don't have, like, energy. It's weird. King Buns says, working on Coca-Cola's broken integration of our product. Oh, that sounds great, King Buns. Oh, God. Hopefully it's not too bad. Again, the name is a placeholder. Can be anything. Let's call it Fungwich today. Why not? Perfect. LenderXT says, what do you mean? CMake is needed for everything. Lamau. We probably will have a CMake target that builds all of our docs, but it's going to be hard to with LaTeX. Suraid says, yup, what's up, Suraid? How going? King Bun says, enterprise devs, let me tell ya. LanderXT says, I was joking. I wasn't. Dun dun dun. What are you gonna do about it? We could totally add a docs thing. How do we use, figure out, there's probably a find package LaTeX or something. There's gotta be some CMake LaTeX stuff going on. Anyway, yesterday we took a look at this paper. King Buns said that he read it and it wasn't too bad, so that's a good sign that it's not too confusing. And he did say there was problems, which I would love to hear. And King Bun says, after installing 30 packages. Lamau. This kind of gets low here. Is this just... Yeah, that's just my viewer. I was like, wait. Where are the page numbers? But they're there. They're there. It's okay. So we were effectively taking a look at this program here. And effectively, we converted it by hand into an AST. And then this AST, previously, this would be used to generate the code. And the problem is it's kind of complex, and it doesn't really have any of the control flow into it. You know what I mean? I mean, there's a while here, but it's not clear where everything happens, what the blocks of code that are running together are. Eternal Wild Fox says, hello, how's it going, Eternal Wild Fox? How's BuildMake going? I'm really curious. You already had C# VS Code solutions being generated? That's so awesome. Thank you for tuning in, Eternal Wild Fox. Eternal Wild Fox says, how are you doing? Thank you for asking. I'm doing okay. Doing okay this morning. I've got too much energy. I think because I ate breakfast and I'm just like, go, go, go. But my body is not go, go, go. My body's like, normally we just sit around, dude. What are you doing? LanderXT said, and that just motivated me to make my own build system. That'd actually be pretty bog. We're gonna have so many new build systems. It's gonna be awesome. Effectively, here is the code excluding the initial declarations. So you see all these initial declarations. We basically just remove those for brevity, but imagine they're at the top here. Probably should mention that, right? I mentioned it a little bit, but probably should mention it more clearly in the diagram. And effectively, our while loop is portrayed with this arrow here. And then our if within the while loop is portrayed as this little branching if here. And again, this technically would be part of this above one, but this input condition would be its own basic block. It's not important. Don't worry about it. It's not the best diagram, but it's our diagram, and it works for what we're trying to explain. Eternal Wild Fox says, I'm doing well. I have to reconfigure some XML and XML schema if that is possible. Ideally, I want to define different project tags for a C# project. Eternal Wild Fox says, lol, Lander. King Bun says, so it talks about how the IR works and what it is doing. How is it literally stored? See, that's the issue. I don't know. Let's go over it, though. Let's go over it. So, let's think about it. I don't actually know, because I haven't implemented it myself. It's it's a work in progress. Ask Sir Aid if you want the best answer. My answer is going to be, I'll define some of the terminology. So basically, here's where we define the basic blocks and stuff. So we're gonna say each box with code within it is referred to as a basic block. And then we're just gonna do something like this. I think I can do that. No? Oh, yeah, snippet is not loaded. That's why. King Bun says, because the AST breaks it down to the lower level logic. Yeah, you're correct that we should have this included. Like, what does it actually look like? But we're going to go over that now. So basically, we have a basic block. King Bun says, so instead of tree nodes, you have basic blocks which operate in a graph. We're getting there. It's still a tree, is the confusing part. The basic blocks thing, still a tree. It's just a directed graph. I can't speak, but it is a directed graph. So there's a flow control, right? A program control flow sense with all these arrows actually being directional. So it would never make sense to go from this basic block to this basic block, right? So this is still a tree. And it's just a directed acyclic. You could call it a graph, a directed acyclic graph. But it is cyclic, I guess, so it's not acyclic. It's just a directed graph, if you really want to be technical in math. And how that's implemented is a basic block is a list of IR instructions, right? A flat list that are of IR instructions, right? We'll just go with that, a flat list of IR instructions. And then we have what's called a function as well. And this is basically a list of blocks, flat list of blocks, basic blocks, with an entry and a return block. With at least an entry and a return block specified, although they may be the same. I think that's fine. We'll put these on new lines, just for us to read a little better. Okay, so effectively, yeah, trees can't be cyclic, right? Yeah, technically that makes it a graph, and then you have edges and everything to worry about, but it's basically a tree. It's a tree with circles embedded for control flow, right? But the actual data structure is just flat lists. It's mostly linked lists. If we take a look, so if we do, I didn't write this code, so I'm not like the smartest person to ask about it, and it's not complete, so don't treat it like this is the be-all and end-all. But here's our actual function. So you can see that it has an entry, a last, and a return block. I'm pretty sure these are the same, but I'm not sure. Maybe there's something semantic here that I'm not certain about. Again, that's where it comes down to the implementation. I didn't write this. I'm sure it's needed, and I'm sure there's an explanation. I just don't know it. A basic block, you can see, is within a function, right? So a basic block is within a function. And what we're looking at in the PDF here is the main function. So we're looking at a single function's basic blocks here. And the confusing part is that this isn't really how the IR looks, right? This is a great way to understand how the IR conceptually looks, but it's not actually how the IR looks at all. So each box with code within it is referred to as a basic block. And then here, I can also say, please, I write pex. I read the pex. I could do something like, what? Each box with code within it is referred to as a basic block. These are the basic blocks of the main function from the example above. Sure. Sure. Is that confusing? I completely understand, though, because graphs are really hard to explain like that in an introductory developer's guide. Yeah. I also just am not that good at graph theory yet, so I'm still learning. I'm pretty sure I have, yeah, I still have like everything open. Look, it was still even hovered over, but I literally have the Wikipedia for graph open. I was reading this yesterday. It's like, I'm still learning, but it's starting to make sense. Basically, we have an undirected graph, which just has any nodes, and we're dealing with these for register allocation. Right now, for the actual IR, it's a directed graph, because everything actually has an arrow in a direction. And effectively, the idea is that these basic blocks store a list of what are called values. Value, I think, has a better name of IR instruction. So when you see value in the code here, I think just refer to that as IR instruction, right? So that's why it's a flat list of IR instructions. So the idea is that we should probably show what the IR would look like, or something that it would look like. So let's define some vocabulary. Let's talk about SSA, a flat list of basic blocks with at least an entry and a return block specified, although they may be the same. There's one more thing I'm missing, which is an actual IR instruction. And this is going to be itine. How do we describe an IR instruction? Basically, an atomic instruction, it's not always atomic. It can be a branch, a compare, and jump, so it's not atomic. I don't know how to describe an IR instruction other than just being an IR instruction. We'll get to that. We'll get to that. We'll go with basic block and function that we define here. We'll put this in and emphasized as well. And then you see them here and you're like, ah, makes sense. So effectively, see how this is still in the center. So these look kind of like a caption. Each box with the code within it is referred to as a basic block. And then it says basic block, flat list of IR instructions. These are the basic blocks of the main function from the example above. So let's talk about SSA then. Let's do the SSA diagram. And then let's slowly move this into an actual representation. Oh look, we even have the vocab definitions. Maybe they should go here. I'm not good at placing them. I'm just going to leave this here because maybe they should be here. So I'll say to do, they are up above, but maybe it should be here. Good enough. The to-do message. Okay. And effectively, what we'd like to say is the above diagram is not what the actual data structure appears as. So let's take a look at a lower level representation of the intermediate representation. How about that? How about that? Okay. So I think this is just going to be a verbatim. That's not how that works. First of all, let's do that. Okay, so let's think about this. This is a lower level representation. So basically we're going to say percentage refers to a temporary, like a register refers to a temporary value, like a register on a CPU. Sure. Sure. That's good enough for me. I think it'll explain why there's a bunch of numbers and percentage signs everywhere. We're going to have to backslash escape all our percentage signs. King Bun says, I also found some very small spelling errors, but I'll just make a PR eventually with fixes. Nice. The diagram above illustrates the basic blocks of the main function in our example program and their relation to one another. That's a much better sentence. I'm just going to steal that, King Buns. If you want, I'll attribute you in a little comment here or anything, but that's much better than whatever I just wrote. The diagram above illustrates the basic blocks of the main function. We're just going to emphasize that because it's a vocab word that's defined right after this in our example program and their relation to one another. That's much better. King Bun says, nah, no worries. I just tried to think of the best way I understand it. All right, you're a legend, King Buns. Thank you for giving us that. That's a beautiful sentence. That's so much better than these are the blocks. Good luck. Yes. So we define basic block, and then we go on to say, here's some BS about it. Not too bad. Not too bad. Okay, then we're going to say percentage refers to a temporary value like a register on a CPU. So it looks like in the verbatim, we don't need to use backslash escape, which is pretty cool. So R0, for example, okay, let's take a look at this. Why am I saying R0? Because this may be confusing. So let's look at the PDF, that'll be easiest. And we can just keep this big. Effectively, when we create A1 here and use A1 here, and then we create E1, for example, for the first assignment of E, and then E2 for the second assignment, another way to think about this is that this temporary value on the right-hand side can be stored in a unique place, but then it can also just, that unique place can be stored into the memory of E. Does this make any sense? LanderXT says, imagine being good at writing in 2022. LanderXT says, or being good at knowing stuff. Oh my lord, can you imagine knowing things? Nexovec says, hello Lens, just passing by to say hello. So good to see you. What's up, Nexovec? We are working some more on basics of graph theory. So if you're interested in that, welcome to the club. King Bun says, I think I need a small elaboration on the memory address storing. Okay. Let me write something. So for example, we're writing B plus C into A1. So what we would do is say, okay, generate some temporary value of B, the left-hand side. This is what we would do in the code gen before as well. It just would be a literal hardware register and not a virtual register. So imagine that R0, right, is B. Well, then we need another temporary with C. That way we can add it into B. So we're going to have to say, okay, so this is a global load. So we're going to do a global load of, what is it, B? Yeah, let's do it. Here, we'll do this kind of syntax. Is this cool with everybody? Understandable? That's going to be annoying. Then we have R1, just a new temporary, could be named anything. And this will be a global load of C. Again, remember that we are skipping some variable declarations at the beginning for brevity, because these are boring and not really illustrative of anything. Sir8 says, oh, you're manually generating IR, I see. Yeah. That way I can explain it to the peeps, and we can have it in the paper. And then, after we manually generate IR, we'll be able to go over how to generate it automatically. It'll be beautiful. Sir8, it's so good to see you. But yes, and by the way, I did some graph coloring by hand last night. I'm catching up to you. This Chaitin-Briggs, I'm starting to understand it. I would be worried. It's happening. So after this, the name of the language has changed again. What? No, it's the same as it always has been. Language, right? Lamau. Anyway, next, we actually have a temporary value we need of A, or A1 in SSA, right? So this A1 temporary value is actually B plus C. So we need some way to say that we have this value, which is like an add. And this we're going to have, well, B, the value we just loaded, and C, the value we just loaded. And would you look at that? We have some IR that represents this little expression right here. And ain't that the coolest? But here's the thing. Here's the thing. Now, you can imagine that this wouldn't be different from the code we were generating at all. If all we do is say, okay, now R3 is a global load of A, right? You could just do this, and then you could say R4 equals -1. This is how we load a number or something, right? And then we could just subtract from R3, R4, and then store that in R5, and that would be our result. The trick is, because also I forgot to do something, we need to do a global store of R2 into A. Totally forgot. Because this B plus C value, this add, actually has to be stored into this variable. That way this load would work. King Bun says, how neat is that? Wait, we are storing R2 or assigned it to A? Never mind. Yeah, you were correct. I missed it. Suraid says, I'm currently implementing the graph coloring part of the algorithm. That's awesome. The reason why my IR representation looks the way it does is because it's meant to look more like an assembly language, since it's essentially abstract assembly. It's true, I just can't, my brain looks at function calls and it knows what it's seeing. And I know that other people do too. They recognize the syntax. So I'm just going for something knowable. Don't worry about changing the output or anything. It's just debug. Suraid says, not just because of LLVMIR. Lamau. LanderXT says, that's actually a decent name. Lamau Funguage. And as you can see, this is our first expression. So maybe I should number that somehow. So this would be expression 10, right? Or something like that. We'll just number it. Does that make any sense in the PDF? Or are we too far away from numbering at this point? I think it makes sense. The numbers are right here, so seeing them here will make a lot of sense. King Bun says, I think it makes sense. Nice. King Bun says, global load, percentage R2A, all in parentheses. Lisps unite. Honestly, I am going to write a Lisp parser for our... We're going to have like a parser for our intermediate representation. It's going to be its own language eventually, I promise. That way, other programming languages I write, I can just use this compiler and just compile them to whatever backends I write here. So if I write another language, I'll just generate the same IR. Because why not, right? King Bun says, the numbers are very nice. I will join for that one. Okay, the numbers are very nice. Let's keep them in then. Thank you for that tip. So then we would have another global store of R5 into B. Is that what we assign to? Am I just making that up? D would be. And also it's a multiply. Add? I think that's fine. Add, multiply. Okay, and that's into D. So here's the confusing part. Our program can still be generated like this without static single assignment form. But the thing is, it converts into static single assignment form because every single value gets its own little name here, its own temporary. Right? So in doing so, we don't actually have to convert our original program into static single assignment form like this. There actually doesn't have to be any splits like this because E2 is just stored wherever it's stored, right? So for example, D1 is stored right here, but it's stored from R5, and if we know that R5 hasn't been clobbered or anything, this virtual register, and because our LLVM are not LLVM, because our intermediate representation is not, it is in static single assignment form. Sorry, I'm just speaking in circles. Because our intermediate representation is in static single assignment form, where each temporary gets its own name, its own unique value, and its unique storage position, this means that we can then start to optimize in that we can use, instead of a global store or a global load of A here, we know that this is actually a use of A1, right? So all we have to do is use the whatever A1 is. We can just reuse that value. Does that make any sense? So instead of doing a global load of A here, you could sense that to optimize it, we could literally just remove this entirely and then just use R2. Because R2 already contains the value of A at this point in the program. Does that make sense? And then upon a reassignment, right? If we ever reassign to A, well then R2 still contains this value of A at this point in the program, even if we end up doing an expression 42, right? If we end up doing a reassignment of A and it's actually a multiply of B and C. Then at this point, we wouldn't have R0, R1, R2, we'd have like R50, 51, and 52, right? Because it's later in the program, more temporaries have been used. And then at this point, we would end up saying, oh, we can just store R52 into A. So then if we ever did a global load of A, we could literally just replace that from then on, right? Instead of creating a new temporary and saying, oh, global load A, we could instead replace it and coalesce these registers. So R53 could actually just be treated as R52. So these could be the same register. Does this make sense? Sir, it says percentage space R50. Oh no. I know it's because Emacs thinks this is a comment. It's not aware of the fancy verbatim package I'm using. King Bun says, this makes a lot of sense to me because of closure in Lisp. I personally prefer to program this way because values don't change out beneath you, but obviously this is harder when you don't have infinite registers. You're getting to it, you're getting to it. So you're recognizing the problem of, oh, R50, R51, we don't have that many registers. If each of these is meant to be a hardware register, how are we supposed to, like, how are we supposed to implement this? And the first issue is doing what we called merging the registers. And effectively, you say that you build your IR and then you coalesce, which is merging live ranges of non-interfering variables related by copy instructions. That's complicated, right? But effectively, all that means is that we can merge this R3, we can just merge it into R2 because it has the same value semantically. So we can just coalesce this register into R2. Is that making any sense? And we can also, also, Sir Aid, let me know if I'm getting things wrong, because I'm stumbling into territory that I just learned yesterday. So if you hear me talk about some things that are definitely incorrect, let me know. And that's also a warning for anyone listening to this. I don't know what I'm talking about, right? I'm trying to figure it out with you, I promise. Eliminating local variables would probably be its own pass before register allocation. I see. I'm just picturing if we just fed this straight into register allocation, but you're correct. You are correct. Where we'd go, hey, we don't need to load A right after storing A, because we know the value of A, it's this. That's fair. So we'll go to 11, and then I'm just going to say ... There should be more, right? And effectively, you can see that even though we still have our variables, and we can load them and store them and do whatever, we also have these temporaries that refer to every single piece of our program. Every single value within our program is stored in a unique register, which is ideal. Everything would be very fast if there was hardware that could work like this. There's not hardware that can work like this, right? So also this would be like basic block 0 or something. So we're going to say BB refers to a basic block within a function. And we'll say fun refers to a function. The following basic blocks are within the function. So this could more accurately be written as fun main with a basic block of 0 ... Yeah. Yeah. Okay, so with this, we can now begin to see, King Bun says, I like it. Awesome. Let's take a look at the PDF. Oh, that looks pretty good. So, yeah, let's take a look at the lower level representation of the intermediate representation. How about that? Percentage refers to a temporary value. Oh, there's not new lines. My bad. We might just want to do an itemize here. I think that would be cleaner. Item? What is it? I always forget. It is itemize. Yeah. Rep string verb item. Yep. And nope. Nearly. On 2 of them it worked. Yeah, then just put these in a box. Thank you. And then, yeah, fix you. Because it's not in a verbatim, we're going to have to / escape it. Percentage refers to a temporary value, refers to a basic block, refers to a function. I probably don't have to say refers to. How about that? Sorry, it says /item /verb, maybe? We could. I don't think it's important that they're in the typewriter font or anything. Looks pretty good. Looks pretty good. Only thing that could possibly help comprehension is a BB0 label on the diagram above. How do we label a node? I know how to label an arrow. How do we label a node? Probably add like another node, but I don't really want to try that. What if we just try that? I mean, we're probably gonna have to do that. Otherwise, it's gonna be on the same line, right? Yeah, that's not great. Sir Aid says, I haven't done any Tixie in a while. Sorry, it says, I think the same way you label an arrow. We could try. How do we label an arrow? It doesn't make sense to me. An arrow is a /draw command. So we'd have to do, just put it after. Just like make another node. Kingbun says node label equals. Does that really work? That'd be sweet. Label equals blah. We'll try it. It did compile. Ooh, BB0. Labeled. How beautiful is that? Also, thank you, King Buns, with the amazing label right away. /node label equals small. Yeah, we can make it small. Is that how /small works? I can't remember. Do I have to do /small in here? I think it's like that. King Bun says yes. He's probably correct. It's small now. Little BB0. We could really just name each one. It doesn't matter. Isn't there another node here? Yeah, right here. I was like, wait, I missed one. Well, let's go for all of it. Also, these names are terrible. I should change them. Wonder if we can change label position. Now we're looking real professional. Oh yeah, this is professional. Real nice. How do we change the label position? I don't know. I don't want to look up Tixie. I'm gonna have to. I don't want to set it more precisely. I just want to set it. Label equals above/below blah colon. Okay. So do I just type above colon and then have a label? Can I do like top right? I'd like not above or below. Can I do left or right? We'll try it on BB4. BB4 I know can go on the top. I just want to see. That works. Okay. That's going to work then. So that's going to go above. This is going to go to the left. It's going to go to the left. It's going to look row 2 of the if. I think that's going to also go to the left. And then this is going to go above. No, above is default, but we're just going to... Also, that's going to have to go below. Screwed up. I think you can do like left equals 4, above equals 1. Oh, like distances in each direction. We're okay. We just gotta fix our arrow now. Also, yes, this is how the arrow works. It's terrible. Don't at me. We're like 6.4. We'll see how it works. Might be a little big. A little further. 420. We'll go 666. Why not? A little too high. 420 is a little too high. I'm gonna go 418. We could probably go to 6.8. Not bad. May be able to go 1 more degree. Yep. That's looking pretty good. Looking pretty good. Oh, Tixie. Okay. We have our diagram now with its labels. How about that? How about that? Oop. King Bun says some fancy stuff. Yeah. Oh yeah. So effectively, we could break all of this down into IR by hand. I don't really want to. So maybe we won't, right? There's a pull request in the Discord to something on Codeberg. A pull request to Lenser OS. Fix formatting errors with license messages. I fixed some not guaranteeing everything of the issues with my license PR, notably with the shebangs being misplaced and the C-style comments being in some of the other file types. What a legend, Lander. What a legend. You submitted a PR, then you submitted a PR to fix the PR. How beautiful is that? Thank you so much, Lander. This is great. I never actually use the shebangs. I never actually just run the sysroots. Like, I never run the shell scripts just by clicking on them. I use the terminal, so it doesn't matter to me. But I appreciate this. I'm sure someone cares about this. And it's probably more legally enforceable now that this is actually copyright to Lenser OS. Thank you so much, Lander XT. I kind of just want to merge this. I gotta make sure it won't, yeah, it definitely won't. Let's just rebase. We'll create a merge commit because of the non-categorical. Okay, this is a totally unrelated, but Lander XT, this is getting merged. Yeah, we're just gonna create it. Do it. How perfect is that? How perfect is that? So we still have this branch, even though we don't need it anymore. Lamau. I'll get to it. I'll get to it. Lander XT says, I didn't expect you to look at that so quickly. I'm streaming. What else would I do? No, but I'm glad it's in. I'm pretty sure there wasn't like code to make everything go really bad. There was no like no hacksers implemented, you know what I mean? Just shebangs and fixed things. It looks perfect. It's in, baby. It looks amazing. Thank you, Lander, by the way. Check out Lenser OS if you're interested. It's an entire OS. There's 1,000 commits almost. Oh my god. It's insanity. Not going too bad, not going too bad. So we define a temporary value like a register on a CPU, a basic block within a function, and a function. The following basic blocks are within the function. See, that makes it seem like these following basic blocks, like there's going to be something coming up. So a function with a list of basic blocks. Yep. So when we describe a basic block, a flat list of IR instructions that must end in a branch. That's probably something we should mention as well. A basic block must end in a branch, otherwise it's not a basic block. That's how they're separated. Eternal Wild Fox says, using XML inheritance now. Oh no. Oh, that's pretty cool, actually. That's pretty pog. Yeah, I know, load XML. How can I split this up easily? That goes there. So this is a project with a name. There's a net version, another project with a type of C. Oh, this is cool. This is starting to make sense. This is very cool. So we have a project with C#, which is a test, and it has a net version. And then we have a project of C, which has a C99 specification. Ooh. W3 2001 XML schema instance is a bit hard to remember, so I'm still looking for another method. You could always just have this be like implicit. If it's always the same in every single project tag, you could probably just have this as like a literal string in your program that it inserts for you, right? King Bun says, you can host your own? Lamau. If you're genuinely asking, then yes. Yes, you can. It's not recommended, but... It is needed in the XML, otherwise the XSI type is not defined. That's what I'm meaning. Like, you read the file not as XML, right? So you'd have to do like search for project tags and then insert this as a literal string in between XSI type. Like if you literally just read regular expression in a file, search for XSI type, go before it by a space and implement this. You know what I mean? Just insert that. It's not ideal, but it's not the worst hack in the world. You know what I mean? Eternal Wild Fox says, oh no. Well, it's better than having to write it every time. I'm sure people will thank you. Okay. So with these, let's begin to go over some lifetimes. So a variable is considered live after it has been assigned. Remember, in static single assignment, there's only ever one assignment to each variable. Again, variable might not be the best word, but we'll say an IR, a temporary, we'll say a temporary is considered live. How about that? Because variable is temporary. Perfect. The range of expressions in a basic block in which a variable is live. So a live range is basically the range of expressions in a basic block in which a temporary is live. Again, this may be incorrect, but this is more correct than it was yesterday. So effectively, when we're talking about liveness analysis, we can keep track of these live ranges, right? So effectively, liveness analysis is done by keeping track of every use of some calculated value in a linked list of use structures. This is done during intermediate representation generation. Effectively, we build our IR with live ranges built in. Let's take a look at what this actually means. Because reading this, I was a little confused, but once you look at it, it's like, oh, that? It's very simple. It's not in CodeGen. What am I doing? It's in IR. Because it's IR. So when we look at, for example, a CodeGen of an add, we can see that it's a, remember value is an IR instruction, is how we can think of that as a better terminology, at least in my head. And see this mark used by, so we mark used by, the left-hand side is used by the sum. And if we go ahead and look at mark used by as an actual function, you can see all it does is create a use structure, right? Remember the use structure that we talked about? Where is it? Here it is. We just create a use structure and then do some linked list shenanigans. But basically, we just implement another use in this value. So this value has been used by this parent. Does that make sense? So every time we use a value, we add to its use list, so it has a list of uses, and the parent refers to that use. LanderXT says, it's in IR, because it's IR. That's right. Lamau. So as you can see, we build our IR with live ranges built in. When we create an add, right? Then all we do is say, oh, the left-hand side is used by the sum, the right-hand side is used by the sum. That's it. Insert this new instruction. Right? It's not too complicated. So when we load a local address, the address is used by the local. The address, right? It's not, nothing here is too complicated. It's actually simple. It's like, oh, when you create one, you just say anything that's been used by it, add to its uses. It makes a lot of sense. So effectively, with these uses, we can then start to use these to construct live ranges, or at least they are the live ranges, they're just not in the best format, or at least human understandable format. So the idea, what do we have next? We have nothing next. Perfect. So the idea is that interference, right? Let's just talk about that. So if two temporaries are live at the same moment in the program, this may not be the best way to say this. King Bun says, so we got to run through and find all of the uses so we can calculate the live range so we don't get interference. Yes, effectively. When we're building the IR, the uses are added to each of the values just as we build it. So by the time we have our IR completed and built, so if we take a look at our little booper, right? We want to build our IR first, right? And in doing so, we also just keep track of all the uses of a value. It may be smart to only keep track of the last use of a value. I'm not sure. Because we need both its definition and its use. Its definition is itself. So it seems because of static single assignment. So what this means is that maybe we only have to keep track of the last use, but I'm not entirely certain. We'll have to get to that. And we'll have to figure out what the last use is first. King Bun says, we build the IR first, then the SSA IR. Not quite. The SSA is actually just a result of how the IR is built. Does this make sense? So this is actually where the static single assignment happens, and it happens to these temporaries. So these temporaries only ever get assigned to once. That's what we're talking about with static single assignment in our intermediate representation. The fact that these values happen to be loads of existing global variables, or an immediate value, or a multiply of two other temporaries, it doesn't actually matter. Each one gets its own temporary. King Bun says, yes, I was just curious how we track interference without knowing the live range beforehand. We don't. So effectively, King Bun says, oh, yeah, so effectively, see how this R3, it's used here, but then it's never used again. Because if we look at expression 11 in the PDF, right, it's actually just D equals A times 1. This A times 1 is never used again. There's not an A times negative 1 in this program ever. So the last use of this variable, this temporary, is going to be right here. King Bun says, oh, that's the next step. Exactly. So you can see that R3, its last use is here. So we during building it, keep track of all of its uses in itself. So R0 says, oh, I've been used here in expression, you know what I mean? Not 10 anymore. We're gonna have to start naming these like A1, A2. I don't know how to refer to these perfectly. We'll say just the R0 definition, right? So the definition of R0 is here, and there will be never another definition of R0 in the entire IR. So the point is that R0, this global load of B in our program, right here, it is never actually used again. It may be, but it's not, right? We actually just reassign to B1 and create this new thing that's then never used. Beautiful, isn't it? So effectively, this temporary, because it's never used again, this is its one and only use. That means it is its last use. And that means that its live range goes from the definition of itself, R0, to its last use right here, which is in the definition of R2. What does this mean? Why is this important? Why do we have to keep track of when it's alive, not alive, but when it's live and when it's not? Why does this matter, right? So the problem lies in this. So if two temporaries are live at the same moment in the program, they cannot be represented They cannot be stored in the same hardware register. Let's say this not backwards. If two temporaries are never live at the same moment, at any given moment in the program, at all moments within the program. So if two temporaries are never live at all moments in the program. So basically anywhere in the program, they cannot overlap. I think that makes sense. They can be stored in the same hardware register. That is, they are said to not, and then we'll say interfere. Interference refers to two temporaries that that are live at a similar moment. I don't know how to say this, at the same time. I don't think that makes a lot of sense. I don't think that's the best way to say this. I wish I was a better writer. Interference refers to two temporaries that are live at the same time. That doesn't really make sense. So we'll say two temporaries that are live at the same time are said to interfere. Yeah, that's effectively what we just said, just the reverse of it. I think I'm fine with it. Jesus, I'm jumping all around. I'm sorry. Okay. Sir 8 says, two values interfere if either one is live at the definition point of the other. Alternatively, two values interfere if their live ranges overlap. Right, which is effectively what this is trying to say without using words that have been made up for this problem, like live range or interfere. But I get your point. I like the if either one is live at the definition point of the other. That's a better one. The former definition is what's used by the RA. So let's try and say that then. Let's use that definition. So we'll say if a value's definition, okay, yeah, so if a value, if an IR instruction, is that what we're calling it here, is live, right, is live, we're calling it temporary, that's what we called it, if and temporary, if the temporary is live during the definition of the other, the two of another temporary, the two temporaries are said to interfere. I like that positive definition. Rather than they are said to not interfere with this, they're said to interfere. So if a temporary is live during the definition of another temporary, the two temporaries are said to interfere. That's a pretty good one. That's a pretty good one. King Bun says two temporaries are said to interfere if they both exist during the live range of one of the temporaries. Yes, so basically if their live ranges overlap. Let's take a look at let me draw a little thing. So we're looking at this code right here, right? Yeah, I think this makes sense. So we're looking at this code here. Let's specifically look at a piece of it. We're going to look at this right here. Yeah, sure. We'll look at that. These four pieces. Just the one expression. I don't know if this is going to go here. I'm just writing this right here. So effectively, yeah, let's just do a verbatim. That way we can still compile everything. Effectively, the live range of R0, right? Oh god. So let's try and let's number these, right? So we're just gonna give them letters, alphanumerics, right? And we're gonna say A. So we're gonna have R0, R1, R2, and I think that's it. And then we're going to have A, B, C, and D. Okay. Effectively, we are saying that this is the four expressions, A, B, C, D. So imagine that these expressions are just to the left here. And in fact, they could be. But I don't want to get over to the right over here and do too much in the comments. So effectively, we can say that the live range of R0 ends at the X and starts, and if there's a line, it continues, right? So let's figure out where it starts and where it goes to. I would say R0, its definition is in expression A, right? So that's where it would start. And it's not, it's used presumably later in the program, so it doesn't die right away. If it's unused, it should just be dead. And that's how you can do dead code elimination. But for now, we're going to assume it's used. And as we go through the program, we have R1. R1 is defined at B, expression B. So that's when this would start to come alive. King Bun says tree shaking. Lamau. And then you can see during C, this is when R2 comes alive. So, boink. So now we have three temporaries that all come alive at some point. But you can see that R0 is not used during expression B. But it is used later in the program. So this means that its range is extended because its use is actually in C. So we have its latest use in expression C. So it lives all the way from A to C. This is its live range within the basic block. Does this make sense? Hopefully this makes sense. R1, like R0, is used in expression C and also lives to expression C, is no longer used. R2, which comes alive during expression C, is then used the last time in expression D, at least in this little snippet. So R2 dies here. So really we don't even need to specify when it dies. That was just for us visually. So the live ranges, you can see, are represented as these kind of candlesticks. And if you then draw lines, right, for horizontal lines, you can see there's one candlestick here that you run into as you go across. Here there's two, here there's three, and then we go back to one. This number represents the amount of registers that are needed to be allocated to represent this IR. Does that make sense? So right now we need 3 registers. King Bun says, yep, so we can't have 16. Here's the thing. We can't have 16 because like some of those 16 are the instruction pointer. I think that's 17. But like the stack pointer and the base pointer, those are reserved for like specific uses. So we technically only have 13 registers that are actually like 64-bit and we can screw with. And then of those, a lot of those have like specific semantics of like RDX and RAX being used in division and RCX being used in string instructions and also stuff like that. So when it gets to hardware, it's there's actually 13 registers we can use basically. And of those, it gets pretty complicated. But effectively with these live ranges, a human can easily go, oh, we need 3. And oh, if we pick RAX for this one, BX for this one, and CX for this one, then that's all, then everything's done. You can just assign 1 to 1, right? Everything's hunky-dory. The issue becomes, if you can imagine, when we copy this, which I should probably copy it from the same place I did up above, which is somewhere here, right? If we were to extend this and go to like, I don't know, A, B, C, D, E, F, G, and H, you can see how these live ranges start to become very complicated, right? We can just move these over. We're gonna have R4 and R5 now, and R3 comes alive during E, F, G, H. So R3 comes alive here and is used in G. So let's just write all of those all the way to G. And you'll see that this little pattern here is actually just going to repeat, where we end up with this. And then something like that. And you can see that a human, once again, we can just count the candlesticks and go, okay, this is easy. We only ever need 3 scratch registers still. It's very intuitive to a human. Doing this this actually on a computer is kind of tough. Is as it turns out, because this is register allocation in a nutshell, and it's kind of tough. King Bun says, I can see. Yeah. Because intuitively, this is like, oh, it makes sense. You need 3 right here. You need 3 right here. You only need 1. Everything's simple. And with these live ranges, right? Oh, man. So I think I'm going to remove these and just have them be kind of implied. Okay. So I'm just going to label and say live ranges from above excerpt. Excerpt from handwritten, from demonstration IR above. Perfect. King Bun says, what's the preferred method to track this? Well, here's the funky thing. If you go ahead and Google Chaitin-Briggs register allocation, this is what we're talking about today, if you didn't know. If you Google it, right, safe search off, no pussy, right? You gotta go full. You can see that you get a lot of PDFs from universities, right? And if we read some of these, King Bun says safe search off, of course. Yeah, what are you, scared? No, but as you can see, the actual process of register allocation, there's not many examples. It's very conceptually laid out. Like, oh yeah, this is how the idea would work, right? This is how it could work. Supposedly, the math checks out. But you'll notice there's no code here. This is not a programmer who wrote this. King Bun says, good luck. Sarade says, as I said, I've yet to find a good example of it online. Exactly. What does this diagram even mean? Sarade says, luckily I have a book that explains it. It's true. And it's even then, it's not ideal. Like, it's very confusing. We get into integrals very fast, and it's like, I'm not sure if I want to deal with limits while I'm just trying to allocate registers. You know what I mean? Like, integrals are not fun. And this is the most code you'll ever see. Def T, store T, load T, uses of T, back here. Like, I'm not sure what the idea is. Arusia says, well, if you want something written by a programmer, look for the source code of a compiler and read that. I mean, let's. GNU Savannah, GCC. It's doable, right? Where we at? Show me the tree. Where is it? I will go read it. I think we can. It's got to be somewhere. Sources, Git, browser, Git history online. Here it is, tree. Perfect. Okay, so now let's just find it. Where is it? It's probably in CP. I don't know. Let's take a look. Register allocation. It's probably in the back end, so it could be in actually libgcc itself. I don't think it's in libgcc. No, libgcc is the runtime thing. I can never remember the data, the tree structure of GCC. There's so many folders. There it is, GCC, not libgcc. Okay, and as we take a look, where are we at? You know, it's just a simple compiler, a little bit of source code. Do we have register allocation anywhere here? Reg notes, reg stack, reg c prop, reg info, reg rename, reges.h. How about that? Rusia says, was only a half-serious suggestion. The code is even harder to read than the slides because compilers are so advanced nowadays. Nah, what? This is totally understandable code. Yeah, easy. Yeah, nothing here complicated at all. Easy code. This actually is fairly scary. There's a lot of macros. Saraid says, ah, yes, the GCC RA. We've made it. But it's not readable, sadly. So all we have is like slides from mathematical professors. Also, Emacs is freaking out. We have slides from mathematical professors, and we have, yeah, that's it, right? So if you're wondering what the best way to do something is, definitely don't ask us. But how we currently store live ranges, like we said, is each value keeps track of its uses. So when we look at a value, you can see that it has a use pointer uses, and that's just a linked list. And its latest use in mark used by, which we took a look at earlier, is added as its first value uses equals this new use. Does that make sense? We basically extend the uses list each time. So this uses pointer of a value or an IR instruction, right, will refer to its latest use within the program just kind of naturally. So the way we refer to it is R0 is a value, and it lives, its use is here, its uses pointer. King Bun says, I think I found the 192-page original thesis. Gonna cry, be right back. Lamau. Suraid says, LLVM's RA isn't any more readable. I mean, it's more readable, but it's still a lot of code. Yeah, let's see if we can find it. What do we get? We probably have to... How to write an LLVM register allocator. Perfect. Yeah, just, you know, easy. Use C++. So funny. Oh boy, more slides. But it's written by a programmer. So it's hopefully that's good. Oh boy. Oh boy. Insert spill fill. This is talking about techniques when spilling. What about just techniques for generic register allocation? They don't talk about it. They're like, they just assume you know how to do it. They just keep giving different examples. Move code around. That's a good example. Lamau. Sir 8 says, this is just the register coalescer. Perfect. Oh yeah, this looks like LLVM for sure. Sure. Oh yeah. Much more readable. This is not readable at all. GCC was much more readable. I could at least understand what was going on. This is just a class. It's a namespace. Oh my god. So we have a class. Oh my. Oh no. Oh no. Sir Aid says, look at the scroll bar. Oh, I know. Yeah. So, obviously it can be tough. So yeah, this is generally how we do it on the right here. And yeah, this is what we're aiming for. Hey, look, live ranges. They're talking about live ranges across basic blocks, it looks like, which is awesome. Arusia says, oh, even the JDK isn't that bad. The Java development kit. Yeah, you're probably right. It's just, it's not as complicated of a problem, you know? So if you're wondering how to do it, so are we, right? Otherwise I would tell you. But we're going to figure it out together because it is happening slowly. So in our IR, we keep track of our uses. So each value, right? Each of our values, our IR instructions, knows when it's used. So for example, this would just go unused because You can never use a global store. It doesn't return any value, right? So even though this is an IR instruction or a technical value struct with an IR instruction type, it does not always have a use. And even if you create a variable that is then unused, well then all of them will actually be unused, and you can say all of those are not needed. With this little used structure, while we can also calculate live ranges, we can also calculate or begin to build dependency graphs. Now, supposedly, we're meant to create an interference graph, right? But I'm not exactly sure what this means yet, so I don't want to go into detail about stuff I don't know about. Effectively, we want to be able to know, so like in our current IR, when we go, the actual IR is done. This is it. This is the IR. We keep track of variable liveness. It's all cool. Right? Everything is, it's just like this. This is the IR. This is the variable liveness of the IR. This is before register coalescing or any optimizations whatsoever. So it's still just a very dumb IR. Also the spaces. Oh no. Cursed. Sir Aid says, I just got done implementing graph coloring. It's not done, but let's see if it works. Oh, that's so pog. That's exciting. That's actually really cool. I'm excited. I'm so excited. Sir Aid. Your next chat message is, I'm hanging on it. I'm hanging on it. Not from there, from here. That'd be so cool if we can look at a working example. That would actually be pog. We were joking about that yesterday, that it would be done by today. If it's actually done by today, that'd be pog. Sir Aid. Okay, so with these live ranges, we begin to understand, okay, R3 is not going to interfere with any of R0, R1, and R2, but these do interfere, right? So to me, it seems like the data structure we should build would be a list of things. Again, this is not right. Sir Aid says, it seg faulted, so we'll see. Lamel, exit with code 5, it's perfect. It works. It's actually, it's in line with how the compiler has worked before. I love on your IR branch, if I feed it any code that isn't just like super simple, it's just exit with code 5. It's so beautiful. Sir Aid says code 139 in my case, lol. I don't even know what Eno that is. On Linux. 139. Whack. That's whack. So it seems to me that we would have to build data structures that refer to groups of variables that cannot be represented with the same thing, right? This is just my intuition. This is not correct. This is not what you should do. I'm just guessing. So let's do it. Sir Aid says the shell reports 139 if it catches a sig-sag. Interesting. I don't seg-fault a lot on Linux, ironically. Normally I buff out all the seg faults on Windows. And then I go, oh, it works on Linux too. So it seems like we need some list of things. To me, it seems like we need lists of things that can't go together, as the length of these lists could then, right, that can't go together. I think this makes sense. So when in doubt, hash table your way out, Ping Bun says, Lamau. Hash tables are so scary. Just requires having the correct input data. That's all. Seems like we need lists of things that can't go together. What do I mean by this? So effectively, because there's 3 candlesticks here, all these live ranges overlap. So when we're building these lists, we would start with our first and say, okay, let's look at the next one, R1. Do they overlap? If they do overlap, add them to the list, right? So we'll start with R0. So we'll have a list for every single one in the thing. Again, this is not correct. This is what I am thinking. Suraid says, found the seg fault. I was incrementing the wrong loop variable in a nested loop. Ooh, I do that so much. Suraid says, now I'm getting a floating point exception. That's a good sign, because we don't use any floating point values, so that's a great sign. That's a great sign. Lamau. King Bun says, values that can't be in the same live range. No, each value has its own live range, right? So they can't all be within one. So I would call this like interfering variables, interfering temporaries, right? Lists of interfering temporaries. Sir Aid says, ah yes, as I suspected. I was dividing by 0. Lamau. That's always how it works. LanderXT says different error. Lamau. That's right. You fix an error, you get a different error. So we're basically collecting lists of interfering temporaries. So when we're going through R0, we're going to go, oh, R1, that interferes. These live ranges overlap 2 candlesticks, right? So we're going to add R1 to our list. Again, we don't need to do this for every node, but I'm not sure how we're going to end up visiting every node. So then R0 will check against R2. R2, again, has an overlapping live range. So what we will do is add it to the list. At this point, we'll loop over R3, R4, and R5, but there is no overlap. So they do not get added to the list, right? So we could say R1, R3 interfere. And then we could say R0, R1, R2. From this, right, we can reason if these interfere and these don't interfere with these, then this does not interfere with any of R3, R4, or R5. Is this starting to make any sense at all? Interfere. This means it's not in here. Blah. King Bun says, isn't there technically an interference range, just like there is a live range? N squared, oh baby. Correct, N squared. This is actually an N squared problem at worst case scenarios. In best case, it's like N log of base 2 of N. So it's not that bad. But this is a complicated problem. In any case, there probably is technically an interference range. I don't know what that is. This is not what we're referring to here. N log N is great. Yeah, it's N log base 2 of N. It's not N log natural log. It's not ln or log base 10. It's base 2. It's not the best. It's okay. So then we can go over R1, but the problem is R1 has already been merged. So we've already actually dealt with R1 and R2, right? So because we've merged them into this list, we no longer have to deal with them as their own lists. How about that? So now R3 we can start on and say, okay, do the same thing. Does it go to R4? It does go to R4. Does it interfere with R5? It does interfere with R5. And then we can say these interfere. And what we could say is, this means that, what effectively does this mean? So with these lists of things that interfere, so with these lists of interfering temporaries, we know that we will need at least the length of the longest list amount of hardware registers. Does this make any sense? King Bun says, but don't these only interfere for a subsection of the program? Best case is we need less than 2 registers. That'd be O of n because they have a separate check for that. That's true. King Bun says, don't these interfere for only a subsection of the program? So I think you're referring to basic blocks now. Remember that this is within a basic block within a function. So a basic block, we can keep track of our live ranges within a basic block very easily with this sort of thing. There are also ways to keep track of live ranges across basic blocks. And that's what happens when you introduce the if, for example. So if we look at our PDF, this if, this means that we're going to have like multiple basic blocks that we're going to have to allocate registers between, because as you can see, E1 can live down into this range, or it can also live down into this range, if that's making sense. So across basic blocks, E1 will live to here, it'll live to here, and then E2 will actually live all the way back up till E2 gets assigned again because it never gets used, so it's actually just dead always. King Bun says, oh, it's only a basic block, big brain. Yeah, but that's a later step to calculate? I don't think so. No, all that is still stored in the same data structure of our uses and our value. It's just semantically treated differently, right? Finding the latest use means that you have to follow control flow, which I think is even what he calls it in the code, like follow control flow, which is probably an RA. Yeah, see, so we can follow a control flow of a basic block. So you can say, okay, where do we go next? And then we go, oh, our next block to branch to is actually this true branch, if it's an if, or it's the false branch, right? Or it can be the branch target, if it's actually the end of the block, the unconditional branch at the end of a basic block. If it's a return, there's actually nothing to do. There is no control flow to follow. King Bun says, but you have to follow the entire flow of blocks to ensure there is no more uses. That's right. And guess what? That control flow that you follow may end up right back where you started. What then? Right? What then? So there's a lot of interesting little problems. King Bun says, I want a lawyer, that's what. That's a good idea. So if we collected list of things that can't be stored together, then with these lists of interfering temporaries, we know that we will need at least the length of the longest list amount of hardware registers. So in this case, we know that because the longest list here is 3 temporaries long, then we need 3 hardware registers. And as a human, that lines up with what we see with this program. B could be stored in register A, C could be stored in register B, right? So R0 could be register A, R1 could be register B, R2 could be register C, because it has to add A and B into a new value C. But then we use C, and then we could just reuse register A again, because we don't actually use R0 ever again. So then we can just say, okay, R3 is assigned register A, R4 is register B, and R5 is register C. Then you could store C into this global variable, and everything is cool. Sir Aid says there's a problem on line 666, lol. That's how you know. That's how you know you're doing the right amount of programming. If you're getting devil errors and warnings of like, this is Satan's work, turn back. That's a good sign. That's a good sign. Line 666 is always good. It'd be best if it's an assert, though. If you get an assert on line 666, that's a win. So with these lists of lists, we can say, okay, we know what is actually going on now. How is this a graph? Like, how is this graph theory? Right? And the issue becomes, I think we should, so let's find lists of non-interfering temporaries, right? Let's find things that could all be stored in the same register. So rather than finding things that can't be stored in the same register, so find lists of things in that can't be stored in the same register. Sure. Whoa. Not sure how I just did that jump. Oh, I did it again. I'm not sure what I'm pressing there, but I did do it twice. So let's find something that can be stored in the same register. How about that? So if we were to think about this, then this means that if we were to look at R0, then we can say, okay, R1 and R2 cannot be, but R3, R4, and R5 can. So we would have R0, R3, R4, and R5 all able to be stored in one register, but we can't actually do that because these interfere. So in finding this list, oh boy, this means we're going to have to both loop over each one, and then each one we find, yeah, so for every item within this list, we're going to have to check that the values do not overlap with the following ones. So R0 and R3 do not overlap, right? And as soon as R0 and R3, then we kind of merge their live ranges. So let's imagine a merged live range, if we can. So I know this is kind of confusing. Maybe we should probably do it in one verbatim. And I believe this is Sir Aid's idea of webs. So then we have web 1 is just what let's call it web 0. And it has R0, right? So let's call this all the way down here, web 0. Perfect, right? Again, this is not final documentation. This is just me figuring stuff out, right? King Bun says, this sounds like it can be an extremely confusing bitmap. You're correct. You are correct. And then you can see that we stored R3 in it because these two overlapped. But then we got to R3 and we figured out, okay, we can store this. How about that, right? So now we have like this merged live range, which isn't discrete, isn't continuous, it's discrete, which is kind of an interesting thing. But this is just because this is R0, this is R3. So in checking, we'll loop over each of these and ensure that the next value that we're checking against to add to the list, like after we're trying to add R4, we'll say, well, it doesn't overlap with R0, but it does overlap with R3, so we cannot do that. So we effectively merge the live ranges. After doing so, we can then do a similar technique with R1, and R1 will start at R0 once again, right, rather than starting past R1. So R1 will go R0, okay, overlaps, R2 overlaps, R3 doesn't overlap, right? So then we would find R3, and then R3 overlaps with the rest. Is this starting to make any sense? I'm pretty sure this is how this would work. Register 2, we could also see, would also just get R3. So what this tells us is that any of these registers could be stored in R3 could be stored in the register of any of these temporaries that we choose to allocate to any of these temporaries. Hopefully this is starting to make sense. So then when we go R3, again, we'll get R0, R1, R2, blah, blah, blah. We'll get those, the inverse, but assume it's unordered and we don't, right? So then with R3, you can see there's actually nothing. So it will just be its own web because we don't want to just produce the same webs in the opposite order, right? Assume that R0 and R3 is the same as R3 and R0 because it is. These are unordered sets. So the idea is that with R3, we actually get nothing. Oh, why did my cursor move? I scrolled up too much. So with R3, we just get itself because it overlaps with the rest. R4, we get the same thing, and R5. But we also get, again, for register 0, we'd say, okay, create one. Okay, we got R3, but we didn't loop over all of our things, all of our registers, our temporaries, I should say. So then we'll continue with R0 and find more live ranges, right? So the idea is that from R0, we would also find R4, and we would also find R5. So what this tells us is that any of these temporaries could also be stored in this register, whatever register we allocate there. again, these would be this would complicate things a little bit, right? Because R1 all of a sudden would also get R4 and also get R5. So then, once you generate these webs, right? The problem is this tells us what we can't do a lot, but not what we can do a lot. So we would have to effectively figure out which of these webs interferes with each other. And we'd have to pick non-interfering webs and assign each web its own register. Does this make any sense? Okay, so effectively... So we want each of these webs. These can be stored in the same register, these two values. But these two and these two cannot be stored in the same ones. So we kind of have to do a cross-referencing. King Bun says, yay, I now understand the high level. Not yay, yeah, Lamau. I can't read. King Bun says, but sheesh, this sounds like a headache. Welcome to register allocation. How may I take your service? You're correct, it's a headache. So effectively, we have to figure out, okay, what are all of these? And then figure out interfering webs and choose ones that don't interfere while also covering all of the temporaries. How fun is that, right? Also, this may all be incorrect. Remember, I'm just talking. I'm just figuring this out for the first time. This isn't something I know. Sir Aid says, in response to King Buns, but sheesh, this sounds like a headache. It is. Yes, it is. It's a headache we're going to figure out, though. So the idea is then we could say, so because W0 is R0, R3, and W1 is this, we can say W0 and W1 interfere because R0, do they interfere? Yeah, because R3 and R4 interfere. So basically, if any item within the web interferes with any other item within the web, so let's take a look back at our little web example, right? Let's bring this down as well. We'll call these webs. Probably should just emphasize it. Oh, also, that's the incorrect thing. Go place this first. So probably like here. And then we'll call these webs, not these. Yay, so high level. Now we have to get, basically we figure out the live ranges and then we figure out, can we store these temporaries in one register or do they have to be in separate registers? And once we start to figure stuff like this out, then we can figure out, yay, let's assign some registers to all these temporaries and then you've done register allocation. King Button says, so wait, could this be a list of bit masks that you can use to compare? It's an adjacency matrix, is how it's actually implemented. I could run it if you want. So if we take a look at like, is this gonna work? Not quite. Lamau. Is that like a 3D bit mask? Sorta. It's basically a matrix. So I would love to show you, but I can't at the moment because the it doesn't work, right? Yeah, that's great. Let's see, factorial. Yeah, nope, that's not gonna work either. Comparisons? Nope. Okay. So Rage says, just do a git reset or something. I know, I don't know what I changed. So it should still work. You know, it should. Yeah. I dump IR. That's probably the issue. Instead of dumping a thing. Nope. It just says could not free the given context. I don't care if you free it or not. It just still says could not free. Don't free it. God damn it. Probably know what it is. Yep, I figured it out. So there's an invalid return there from a void function that I removed. We still don't make it. Fuck. Man. Invalid value type. That's not my fault. Okay. Invalid value type. I don't know how to fix that one, honestly. I got tricks for the other ones. Please. Just show me what... Nope, code 116. Pretty sure that's a, like, stack execution in Windows. That's not good. You can always just reset the branch. Why, though? I didn't... It worked yesterday. I didn't write any code, and now it doesn't work. I renamed that to quotient. There's a printf there. And there's fixes in this that weren't implemented, that we talked about. Why would this be here? Why would it exit 0? That was my question. Just because in the debugger I was running it in. Hey, we did it. We have to exit 0. Wonderful. Don't you love half-done programs? But hey, we're going to be able to look at it now. Here's the adjacency matrix. Where were we? Tech. So here's the adjacency matrix. And effectively, with these webs that you build, right? Each of these webs, web 1, web 2, web 3, web 4, web blah. Then effectively what we can do is say, do these webs interfere? Is our next question, right? Sir 8 says, update, it no longer crashes. Hey, let me guess, everything gets racks? Hopefully, hopefully it's at least generating code or allocating registers. It's assigning racks to everything, so yeah. Hey, I guessed correctly. Lamau. I knew that's what would happen. That's so awesome. At least it's starting to work. That was my, my crazy goal for today, so we did it. Rax is just the GOAT, says King Buns. It's just the best, man. So it seems like R4 is that. This would be R5. How beautiful. So then we can go 3, 4, 5. And you can see web 3 is R1, so it actually doesn't have anything here. And it goes to R3. You may be noticing a pattern already. How about that? Right? Okay. Jesus. So we'd get to R2, and it could be stored in R3. R2 would also get R4. R2 would also get R5. Right? 7, 8, 9. So this would be something like this. I'm going to need a rectangle copy. Can I do that? I can do that, like that. It's not going to be perfect. It'll work though. Look at that. How beautiful. Yeah, what is this? W6, 7, 8. And there's going to actually be nothing here. Nothing. And these are all going to be the same. But R2 is going to be the one that's being used. So instead of this, this, and this, right, we're going to be down here. Should have kept that. And it's just going to be W6, R2, R3, like that. Oh boy. Perfect, huh? King Bun says, what else can be said? Rex is just the goat. That's actually really pog, Sir Aid. We're beginning to have it work. Also, I don't know if this is correct in any sense, but we're doing it. So R3 again would get R0, but we already did that, so we don't want to do what stuff we've already done before. So we're gonna do R3 and R4, R3 and R5. We can't, so we just get R3. We would just get R4, and we would just get R5. Does this make sense? So R5, we could assign it with R5, R2, R1, R0, but that is equivalent, because these are unordered sets, to R0, R5, R1, R5, R2, R5. So these edges, effectively, have been created, no matter what. So, with this, how does this actually make any sense? Let's look at web 9 as R3. Is that R3? Yeah, I think it's up one. Okay. And then web 10, again, web 11. So this is R4. And then we have R5, so that's W10, that's W11. And you can see that these webs are actually identical to these temporaries. So each of these temporaries are actually going to get their own register. And what we've learned is that each of these temporaries can effectively be stored in other temporaries, or other temporaries can be stored in this. So what we know with all these webs is that R3 is actually the same as R1, or the same as R2, or the same as R0. So to figure this out, we have to figure out the web's interference. So W0 and W1 webs interfere because R3 and R4 interfere. So W0 and W1 here, right? You can see that they interfere in that they line up, they have non-identical temporaries. Are the R0, R5 registers or temporaries? They're temporaries. If that's the case, how did you end up with more webs than temporaries? In the latter case, I mean. So, I don't know. I just made up webs. I don't know if this is actually a web. That's what I was saying the whole time. I'm like, I'm just making this up. We're just collecting lists that don't interfere. Well, right? So we're just saying, find list of temporaries, not things, temporaries that can be stored in the same register. We'll call these webs. I don't know if that's right. That's just what I called it. So R0 could be stored in R3. R0 and R4 could be the same, and R0 and R5 could be the same. That's how I'm getting more webs than temporaries. So how would you solve this issue? Because we have to generate more webs than we actually need, then find ones that don't interfere, no? Or we just have to only create webs that don't interfere with the ones we've already created. So web 1 and web 2 here would never be created because they are... I don't think you're building the webs correctly. That's what I'm saying. But nobody's explained to me what a web is even defined as. So I've been saying this whole time, I don't know what I'm talking about. I think I'm just going to find things that go in the same register. And that's what I've done here. Then we figured out the live ranges. And basically, the live ranges of these webs interfere because the non-identical, right, these are all R0. We don't need to check if R0 interferes with itself. It never will. but the fact that R3 and R4, here and here, interfere mean that we can't use these webs together. So we actually have to discard web 1 and web 2 if we want to use web 0. So assuming we want to use web 0, we can't use these. But we could use this because it doesn't interfere. But I'm definitely doing this wrong. So how would I do it correctly? What are the webs actually defined as? That's all I need. Because I said up here, I'm like, at this point, I no longer know what I'm talking about. It explains how webs are constructed. It doesn't help that much. We'll take a look. So, again, this means temporary is what he's talking about. Certain temporaries overlap and can share a register, blah, blah, blah. So it says phi and copy nodes are webs. Why? Why is it only phi and copy nodes? Like, aren't there more values that can be stored in the same register? That's what's confusing me. The comment at the very top is all you need. So if they can definitely share a register if these aren't true. Is that right? I'm not sure how that would be the only rules. That confuses me, because these don't follow those rules. This is a temporary. This is a temporary. They don't interfere, so they can go in the same register. No? So how does a copy node or a phi node have anything to do with these being related? Webs are not about interference. What are webs about then? Why would we need to calculate webs? If we need to have interference of registers, and that's the only thing that says whether they can have the same register allocated to them. Webs are about what values must go in the same register. Right. We're saying the same things. Or you're saying something different and I'm not understanding you. In either case, it's not working. How can R0 and R3 have a phi node or a copy node, like have anything to do with these two separate things? Because R0 is a global load, R3 is a global load, but they don't actually need to go in the same register, right? Sir Aid says, all right, just wait a second. King Bun says everything must go in racks. You're correct, King Buns. At least that's apparently how Sir Aid's implementation currently works, so we'll see. I don't think we need this. It seems like this would be a much easier way to do things, by the way. Just making lists of interfering temporaries, than just assigning each one of these lists their own registers. Oh, this gets racks, bx, cx, etc. Racks, bx, cx, etc. All you'd have to do is make sure all these lists didn't interfere. First time chat from a viewer, Sukantian. Imagine not writing the compiler in binary. Shaking my head, my head. Oof. What's up, Sukantian? Thank you for tuning in. Shaking my head, my head. So effectively, these are apparently webs, because webs are values that must go in the same register. So these aren't webs because these are values that might go in the same register, not must. Is that the only difference you're trying to specify? These might go in the same register. If you're saying ones that must go in the same register, why does that matter? Why do you have to, like, can't you just do that through people optimization? Why do you have to make it a whole problem? King Bun says could go in the same register. Eternal Wild Fox, does somebody have some idea what should be in a builder program? ISO ready planned planning a zip file or downloading from GitHub. What? Running shell commands. Copying files from one place to another. Generating files. with macro replacement. Or King Bun says, I had an aneurysm reading that one. Sorry, Eternal Wild Fox. It wasn't too bad. He's saying, what should build make, what else should B make do? You had a what? An aneurysm. The funny part is aneurysm is spelled wrong. Also, don't I look like a day trader now? Sir Aid with the major paragraph coming in. Also, Second Thean, thank you so much for the follow. Eternal Wild Fox, if you're curious, an aneurysm is a bleed inside of your brain. King Bun says aneurysm is spelled correctly. With a Y? I don't think that's how we spell it in America. We definitely spell aneurysm with an I, I'm fairly certain. I could be incorrect. Is it really a Y? You would be completely incorrect. Why is it a Y? How does that make any sense? I hate English. It should be an I, and I'll write it with an I out of spite. Because it's short for aneurysmal dilatation. Oh yeah, that helps. So an aneurysm is just a bleed. It's a ballooning and weakened area in an artery. So basically your artery is like a water balloon, right? And the water balloon is kind of stretching way too much. It's a blood clot in your brain. No, it isn't. That's a brain aneurysm. Sir Aid says all values in a web must go in the same register. In SSA form, each value is a web. Phi and copy nodes are special because they merge multiple values. Merging values here means they must end up in the same register. Therefore, values that are connected by phi node must go in the same register. Therefore, they're part of the same web. A value can only be in one web at a time. If two webs intersect, that means we need to use different registers for those webs, but that is determined using the interference graph later on. So what you're saying is, instead of trying to do all of register allocation where we figure out, hey, these don't go together, these don't go together, you're just trying to make it a little more simpler. Like, what are the ones that are for sure in the same one? So you're telling me we would have no webs? Or all of our webs would just be equal to a temporary? And then we would go on to do our interference stuff? Is that what you're saying? So effectively, this wouldn't exist. Is what I'm pretty sure what you're saying, right? No webs of this manner. In this case, I think each value would be a web, yes. Well, that's... So instead of that can be stored, must. This is going to be text, bold font, / emphasize. Can I do this? Can I do nested like that? I forget how to do things like this. Must be stored in the same register. Yeah, that didn't work at all. I can't find file? What? Okay, it did work. There we go. You can nest them, yes. Hey. I don't know why it couldn't find the file. So, find list of things that can't be stored in the same register. That's not really useful. It seems like it should be useful, but apparently it's not the way to do things. So, find lists of temporaries that must be stored in the same register. We'll call these webs. In this program, there are no copy instructions or phi nodes which merge multiple temporaries from different control flows into a new temporary. So each temporary... See, this doesn't make sense because saying each find lists of temporaries that must be stored in the same register. The thing that's confusing is that each of the webs, they don't have to be stored in their own register, right? So the confusing part is we're like merging temporaries into webs, but then we're going to merge webs further into things that are like atomic with registers. So we're just breaking it down into so many steps. Okay, in this program, there are no copy instructions or phi nodes, blah, blah, blah. So each temporary is in its own web. Like so. Perfect. Something like that. Bunch. Different webs can share a register, but that happens at a later stage of the algorithm. Exactly. When we construct the webs, we don't care about that yet. That's all that was confusing me. I was trying to construct them while also figuring out which ones can share a register or not. But we should split that up into multiple steps. I'm starting to get it. So each of these get their own thing. Webs establish requirements as to what values must go in what registers. That's a beautiful way to say that. So at this point, we will build webs. A web is a list of temporaries that must end up in the same hardware register. So this is when we convert from live ranges into actually talking about register allocation specifically. And this is all useless. This is all useless. This doesn't make any sense anymore. 2. This info doesn't make any sense whatsoever anymore. Perfect. Okay. Webs basically introduce the harsh reality that we don't have infinite registers. See, King Buns, that's what I was thinking, but that's not true. That was my misconception as well. So effectively, a web is a list of temporaries that must end up in the same hardware register. So if you can imagine, okay, let's imagine a little bit of a more complicated control flow, not just within our one basic block, but our actual control flow. And let's imagine one that actually matters. So here's our control flow of our if, right? It can go to the if, it can go to the, or it can go to the then basic block, it can go to the otherwise basic block, or basic blocks, and then it can go, those will eventually branch to this basic block. Eternal Wild Fox says, the white of the PDF hurts my eyes. I've honestly tried so many times to get dark mode PDFs working, but it's just so impossible. I think I just have to invert my screen, which would not be ideal. King Bun says, how do we know that they must? Exactly. So, for example here, imagine if on the left-hand side, we assigned the variable, here, let's go up one. Imagine on the left-hand side, it's not this, it's just reassigning A to B. And on the right-hand side, we reassign A to C. Eternal Wild Fox says, that would be cool, dark mode PDF. I wish. Also, this graph is not entirely correct. There should be another block before BB0, and all definitions in BB0 should be phi nodes. These should be phi nodes? What? Why would these be phi nodes? Is this just to basically, because the declaration created a temporary, and then these are also just a mixture? I mean, it's a new value. I lost you there, Sarade. It's okay. We're just taking into account like there's an if-then. This entire diagram we're not really thinking about. Basically, if there's an if-then where A is assigned to B, and then an if-then where A is assigned to C, if we then down here say C, or like D is assigned to A, which value of A do you use? Which temporary that you created? Because you created one here and you created one here. So which one do you use? Well, you have to use both. So both of those temporaries, also I just said both, kill me. both of those temporaries have to end up in the same hardware register. Otherwise, the code you generate would have to move from one register or a different register based on the things that happen at runtime, and that isn't possible. Sir Aid says, basically, where's the F coming from in BB0? Again, we talk about this. The declarations are not included in this diagram. Sir Aid, please. Here is the while loop body from our current program. This doesn't say here's the entire diagram of our program. It says excluding initial variable declarations for the sake of brevity in the initial basic block. Please, Sir Aid. King Bun says PDF view midnight miner mode. Yeah, that's not going to work. I think you need PDF tools. Eternal Wild Fox says both, lol. It's true. So, yes, it is true. This is not the full IR. We go over this. This is a section of the IR for this diagram, for this example. Otherwise, we would have like a basic block here for no reason that we never reference. Like, we never talk about it. You know what I mean? And it would mean that this diagram would it'd be the whole page. Anyway, the full IR is a bit too complicated for that example. For any example, really, it's too complicated. Lamau. So, register allocation. At this point, we'll build webs. A web is a list of bleh that end up in the same hardware. Whoa, that end up in the same hardware register. So, webs from above excerpt. So, if these were phi nodes, why would a variable declaration be a phi node? That's something that's confusing me, Sir Aid. Shouldn't it just be a regular temporary? Because a declaration should just create a temporary of the right-hand side value that's being assigned, and any values that need to be assigned to calculate the right-hand side value. But then the actual global store, isn't that just gonna, that deals with the assignment? Why would it become a phi node? What values do we have to merge? I am curious. Also, this guy doesn't know what he's talking about at all. He copy and pastes. It kills me. He's like, oh yeah, and here's all the answers that I stole from this book. It's like, oh wow, you know what you're talking about. Wow. So with these webs show that there are no registers, no temporaries that must be stored in the same register. Keep in mind that these webs may still be stored in the same register. May still be stored in the same register if they do not interfere. I think that makes a little bit of sense. Sir 8 says the F in BB0 has to be a phi node because its value is different depending on whether you're entering the block from the block at the end of the loop or from the block before BB0. The F in BB0 has to be a phi node. You're saying, you're talking about the while loop, is what you're saying. You didn't say it, but you're just talking about the while loop. In the diagram where you're using temporaries instead of variables, that is. Yeah, the loop makes everything very complicated. I would agree with you. Because the problem with F being used here, this F access, so you're not talking about this declaration, you're talking about this use. This is now making sense, Sir Aid. This F access, it may be stored in the register from up here, right? Because we have a variable declaration of F. So this, assumedly, this variable declaration has some register allocated to it. And because we need to move from it, right? So assumedly, this is some register. But if the control flow of this control flow, if we get back to where we are and f has been reassigned, right? Or assigned, what this means is that because f has been declared up here and f has been declared here, these two different assignments will actually create two different temporaries. And these two different temporaries, one from up here that we don't mention and one from right here, will have to be merged into this value right here and be stored in the same register. So what that means semantically in the register allocation is that when we assign the value of f, we should store it in the same register as this, 2 times e. I know we never assign f, so that doesn't apply to this program. It's not perfect. We'll fix it. But I now understand what Surid is saying. And the merging happens by using a phi node. Oh yeah, I should definitely mention that. So let's talk about some terms in register allocation. We're going to have some items. Why does that not work anymore? We're going to have a web. A list of temporaries. What are the temporaries that... Also, they're missing a slash. Must be stored in the same hardware register. King Bun says, yeah, this makes sense. I also have a headache. King Bun says, not really, but I think one might come on soon. Drink some water. Surid says, also, be right back, and then I'll take a look at why it's storing everything in racks. Awesome, awesome. If you pushed those changes, I would love to take a look at them as well. King Bun says, will do, cracks Miller Lite. Lamau. I've never been an alcohol person. I'm not saying it's bad to be one, by the way. I'm not being one of those guys. Because that's just boring. It's like, you can do whatever you want. I understand having fun is very subjective. But to me, I just feel sick. I hate feeling sick. But my stomach's sensitive, so it makes sense. So we have a web. At this point, we will build our webs. We already defined this. We will build our webs. So we should talk about phi nodes at some point. We may want a whole subsection on phi nodes. Phi node. A node that represents a merging of multiple temporaries, possibly from different basic blocks. I don't think we need this. That just complicates things. We'll say a node. What is a node? Why do we call it a phi node? Let's call it a phi instruction. We're just going to say, yeah, phi instruction. The phi IR instruction represents a merging of multiple temporaries into a new temporary. Is that correct? Was that... King Bun says, I am more of a 420 person than alcohol to slow down the brain because it is too hyperactive most of the time. Yeah, I don't think I've ever streamed without being a 420 person. King Bun says, so phi nodes are what actually gets allocated a register to use. Close. You're very close. So when we are here, a web represents the phi nodes. So, right, so we have a phi. So at this point, we will build our webs. To build webs, there are only a few simple rules. Can I do itemize? Probably just do item. Again, I wish that was still working. There are only a few simple rules. Okay, and this, I think we can look at this. It's starting to make sense, Sir Aid. Your ways are not so are not so magic anymore. I'm starting to go, oh, that makes sense. So to build webs, there are only a few simple rules when trying. So what does this mean? A is a phi node and B is an argument of A. So when we refer to A and B, okay, so we're referring to build webs, there are only a few simple rules. For two values, so for two IR instructions, A and B, so for two IR instructions, A and B, and then I think we'll just give it like that. At this point, we will build our webs. To build webs, there are only a few simple rules. For two IR instructions, A and B, anonymize A is a phi node and B is an argument of A, or B is a phi node and A is an argument of B, or A and B are both arguments of the same phi node, or A and B are both arguments of a copy instruction. Conceptually, this all tracks. Two values are merged. They should probably be stored in the same hardware register. That's not correct. They shouldn't probably, they must be in the same hardware register. Otherwise, further accesses would require runtime knowledge during compile time. Is it runtime as one word? Is it runtime as... We'll do dashes. King Bun says, oh yeah. King Bun says runtime as one word. Does that mean compile time is one word? That doesn't look right to me. Wait. What is it? I want a lawyer. Brett DeLawyer, a denial corporation. Okay, we could also probably do something like this, just to get better typesetting. As a phi node. Also, I don't like having phi in all caps. Do we need phi in all caps? Phi. We're looking it up. Phi is a Greek letter. I don't think it's in all caps. Phi. Yeah, it's just this Greek letter. That thing. Oh, that's lowercase. We want uppercase phi. Thank you. Can I actually do /phi? That actually may be a thing in LaTeX. It may have to be in math mode, though. We're gonna try. Did it work? Hey, it worked! How confusing would that be? I kind of like it. /phi should be the uppercase one. Nice. Thank you. Bless. Beautiful. Beautiful stuff. Should work without math mode too if I'm not incorrect. Says Ruark. What's up, Ruark? We're looking at some LaTeX. You are correct. If it works without math mode, that'd actually be pretty pog. I just wouldn't expect it to. Yeah, it's mad. It's mad. Cool. So we have phi. The phi IR instruction represents a merging of multiple temporaries into a new temporary. This is relevant during... I'm not even going to go into that here. So we have web, we have phi. I think everybody knows what a copy node is, or a copy instruction is. So I missed these. Phi. Just gonna do that. And then we're gonna say the same thing, phi instruction. A is a phi instruction and B is an argument of A. A is a phi instruction and B is an argument of A, or B is a phi instruction and A is an argument of B, or A and B are both arguments of the same phi node. A and B are both arguments of a copy instruction. Or. Also, this is like a theorem. We should probably have these in like their own theorem. We could use AMS math. Ooh, didn't like that. Where are we at? There we are. Phi, A is a phi instruction and B is an argument of A. B is a phi instruction. So what is an argument of a phi? So phi. The phi IR instruction represents a merging of multiple temporaries into a new temporary. The temporaries to be merged are referred to as phi's arguments. King Bun says, I love that on llvm.org they have a My First Language front-end tutorial. That's the worst tutorial in the world. It makes it sound a little bit more friendly and approachable, like My First Bicycle Ride or something. LLVM has the worst tutorials in the world. They're like, yep, just, redefine all of the LLVM nodes yourself in your own program for no reason. Then all you have to do is boop, 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 call the submit function. It's like, this is not the correct way to build an LLVM front end. This is so messy. And it's so difficult. And they make it seem like, oh yeah, this will be like your first time. This will be great. It's a good tutorial. It's like, it is not. It doesn't explain anything. And it has the most complicated linking and like build environment that you could imagine for your first language front end. It's like, no. It's so bad. For two IR instructions, A and B, they are said to be, they may share the same, they, again, must, is what we're going to say, must share the same register if Bruark says, LLVM is so difficult on its own that I don't see any difference in building your own backend versus using LLVM. I'd say it's simpler to use your own backend than using LLVM. Because when you build it yourself, you don't have to support all this crazy stuff or understand phi nodes or anything. You can just go, I'm going to convert my AST into code. And it works, is the scary part. And it works. Okay, so this looks like it's been cleaned up a lot. They must share the same register if any one of any of the following are true. So for two IR instructions, A and B, they must share the same register if one of any of the following are true. If any one of the following, that's better. Rourke says, Lamau if. It's true if and only if, buddy. So for two IR instructions, A and B, they must share the same register if and only if any one of the following are true. A is a phi instruction and B is an argument of A. B is a phi instruction and A is an argument of B. A and B are both arguments of the same phi node. A and B are both arguments of a copy instruction. So basically, phi nodes and their arguments all get merged into one web. And then temporaries that are copied into each other, created by copy instructions, these are also put in their own web. Rourke says, I see. Yes. So if is short for if and only if. You just type if, and in mathematics, that generally means if and only if. which means that if this is not true, then like this will never happen. So they must not share the same register if any one of the following are not. Does that make sense? It doesn't imply the negation, but it just implies that this is the only way this can happen. Rourke says, yeah, I only have math conventions from Germany. That's a good point. I have a lot of American math conventions. Because turns out I'm American. I didn't know. I figured it out just now, though. Yeah, if two values are merged, they must be stored in the same hardware register. Otherwise, for that would happen during compile time. Two values are copied. Why not just use the same register to refer to both? That way, no actual hardware copy has to happen. The copy can just use the originally calculated value. How about that? King Bun says, most of my client meetings this morning were with German clients. I can't read still. King Bun says, which is great because they want to get the meeting over with just as quickly as I do. Lamau. It always sucks when people want to talk at work. It's like, shut up. This is not what we're here for. We're here to do work, and then it's done. Right? People don't always get that, though. Webs from a Bev excerpt. Stored in the same register. Okay. These webs show that there are no temporaries that must be stored in the same register. Keep in mind that these webs and temporaries and corresponding temporaries may still be stored in the same register if they do not interfere. What is web interference? I'm asking you, what is it? No, it's not too complicated. Webs interfere. If two webs interfere, if any of the values in either of the webs is live at the definition point of any of the values in the other web, what this means is that if any one of the values in web A, okay, two webs are said to interfere if, and only if, let's see, what is it? If two webs A and B are said to interfere if any one of the temporaries, also I think we switched to saying value up above when we should not. We did. I just realized when I wrote temporaries. Starade says, I'm back and I just had an epiphany. I think I'm now at a point where I fully understand the entire workings of the algorithm. That's so cool. Ruark asks, what is a web? Well, interesting that you, fancy that you asked that. We have a little definition right here. And I actually learned this today as well. Sir Aid says, that means I have an idea what was wrong with div, etc. and how to fix it. Oh, that's awesome. That's so exciting, Sir Aid. I'm so glad you're so much smarter than me, so I can just like ride on your coattails and learn all this stuff. It's really awesome. Ruark was asking, what is a web? A web is a list of temporaries that must be stored in the same hardware register. So, for example, when we access F here, we don't know if it's going to be actually this temporary that up where it has been declared, or if it's going to be this temporary where it has been assigned here, right? So if this temporary has been used, then we're going to have to use like R8 or R24, let's say, right? And then if this temporary, the one up in the variable declaration, if that's used, then what that means is we actually have to use R5 or whatever, right? Ruark says, oh, dude, I'm dumb. It's okay. We'll get there. I'm dumb too. If you've been following, I'm literally going, is this right? I'm pretty sure this is wrong. The whole time. I don't know anything. I'm learning from you guys. Ruark says, not anymore, because I get it now. Hey. Saraid says, it took me a few days to understand this, so... Lamau. That's pretty impressive. Understanding graph theory, complex graph theory in just a few days is pretty impressive. But anyway, see this access of f, it may actually refer to different temporaries. So we actually, when we access f here, it has to be a phi node. That may either be this temporary or this temporary that we don't talk about in this diagram, right? So it could be one of two temporaries. And with each of these temporaries, like one of these $R0, or I said dollar, percentage sign R0, percentage R1, percentage R2, each of these is a temporary. So you can imagine that a phi node would say, well, use R1 or use R4, whichever one came most recently. And the only way to know which one came most recently is during runtime by storing them in the same place, right? And to store them in the same place, that means they must go in the same hardware register. So a web kind of lists, it breaks down all these phi nodes and says, okay, these must be in the same register. There are no phi nodes in this little excerpt right now, but eventually we're going to have examples with actual phi nodes and stuff. Ruark says, all of us are dumb. Now you're starting to get it. Sirade says, I just pushed what I have so far if you're interested, but disclaimer, I know that there are definitely some things wrong with the logic here and there. Also, I'm postponing coalescing and spilling until everything else is working. Yeah, I don't care about spilling at all. I don't think spilling will ever happen with our language unless we do some very, very, very bad code that the programmer writes, right? Coalescing is definitely something we should do, but again, it's not needed. And it's only going to make our programs more optimized and faster. And we may even want to disable it in certain cases, like in debug scenarios. So postponing those is totally cool. I am going to pull your new code though. Now we're going to have to do a hard reset. Yeah, why not? Perfect. Now we're going to fetch from all remotes. And then there's going to be some things to happen, I presume. Hello? Hello? Did we not check out the right branch? So I would like to check out a branch, origin IR. There we go. I don't know why why is my head not being updated? I don't know why. I'm checking out the branch, but I'm not actually switching to the branch. How do I switch to the branch? Is that what's going on? I don't even know. I'm confused. I'm too dumb. But in any case, I have the code. Hopefully I can pull it. Pull from elsewhere? No, pull from origin IR. I don't know what I did wrong, but my Git is majorly messed up. What is happening? Head detached. Oh, that's great. That's my issue. Oh, great. Oh, I've read that one. King Buns, I did read that one yesterday. So King Buns just linked this PDF and said this helped a ton figuring out how register allocation works. So that's awesome. That's very cool. I wish I could read it. Fuck is wrong? Why is there 4 on 1? Talking about spilling. Spilling doesn't matter to us right now. Build interference graph. Iterate until there are no... Hey, this is really good. So this is really good because they go through the coloring algorithm without spilling, and the spilling is a useless thing most of the time because you never actually need it. But it's so complicated that to explain it, it takes so much time. This is awesome. But yeah, this talks about the Chaitin algorithm. It doesn't talk about Chaitin-Briggs with all the better spilling techniques. But yeah, while there is spilling, rebuild the graph. Basically, you just have to keep rebuilding and spilling more and more temporaries until you get an amount of temporaries that you have registers. So if we had 13 registers, then we'd have to go down and iterate until we spill until, oh, we're down to 13 registers. We can do this now. Then you basically just go through and color the graph, which is one of the easiest things in the world. They make it very complicated. It's not too difficult. And I'm not saying it's easy on a computer science level. It's easy on a brain level, right? So your brain is like, looks at this and goes, I know how to color it. B can be red, but that means C or E cannot be red, so let's make E blue. C could also be blue because it's not attached to E, but it can't be red, so let's make C blue. So now we have red, blue, blue. Then you can imagine these are both blue, so this one must be red. And these are both blue, so this one must be red. Does that make any sense? So B and D would end up as red, E and C would end up as blue, and A would also end up as red. So bad, red, E, C, blue. And then, yeah, you just color in the things. I'm yeeting all the to-address stuff because I don't think it's necessary. Awesome! That's so exciting. I don't think it's necessary either. I'm happy that that's happened. Because we can yeah, I'm starting to get it. Because the new temporary we create can basically just be an implied web in the back end. Is that making any sense? I think that makes sense. Why is my head detached? I'm looking this up. Head detached. Why? You're not on master, you're on a detached head mode. Yes, can I go back? So it's not a local branch name or if there's a tag. Yes. Oh, Christ. Why? You simply need to switch back to the master. Why? If you wish to fix a bug, you should work at your own branch. Thus, check out the master and branch from it. So it wants me to make a local branch, but this isn't a local branch. I don't even know. I don't know. It doesn't matter to me anymore because we have the code. Hey, look, it's different now. Where are we? Oh my God, what happened? Perfect. We still need to convert a equals add bc into move ab add ac, but the x86-64 backend can do that when it emits the code. Yes, Sir Aid, you are getting it. Just git switch dash, I think, but this could be wrong. I don't care. A branch is expected, got commit. It is, I just had to switch to the branch. Remember earlier when I said I just have to switch to the branch? I knew it. That was my first instinct. I just didn't do it because I didn't want to screw with things. Also, Sir Aid, thank you so much for that tip. That helps out a ton. It didn't work perfectly, but it let me figure out, hey, that's that right there. That's a problem. Actually, that's not that right there. That's the origin master commit. Lol. In any case, hey, we fixed it. Now Emacs shouldn't be so picky. Yeah, it also automatically pulled it during the checkout without switching. How interesting is that? I don't know how that works then. Okay, we are now looking at real code. How long has it been? It's been a while, baby. So with register allocation, we can see that there's webs and stuff. Like, yeah, you know. There's webs and stuff. Ooh, we're not printing out the same things. No longer the adjacency matrix is being printed out. Code.s still not being generating anything. What do we got? Unknown conversion type character L in format? Why are you saying you don't know what LLD is? Okay, I'm not sure why I'm getting these warnings. Either way. The matrix is just commented out, I think. Nice. You're probably correct. Whoops, whoops. Yeah, don't break things. Ooh. Exactly. Yeah, perfect. Prune interference graph. Perform initial graph coloring. Min register. Return the smallest register that can be assigned to the vertex at the given index. Hey, so I was right with keeping track of which register allocation we were doing with just a simple index. That's cool. Yeah, because then you can just implement the next one. Also, very cool bit masking. I would love to figure out, each bit represents a register. If the bit is set, then the register is in use. Also, int max t. That's very interesting. So we just... we might want to define our own type here. That's just typedef to int max t for now. But that way, if we ever have something where it's like, hey, we need to actually support a certain amount of registers, like 256 or something. This would be in the future for a RISC architecture, I'm sure, but it's now regmask t. I already made it a typedef. Sir Aid, you're a legend. King Bun says, I was right! It's a bitmask, gang gang. Sir Aid says, it's just not in this commit. That's beautiful then. Sir Aid, you're a genius. You're one step ahead of me, at least. Assign registers to each vertex in the interference graph. Returns 1 if the graph was colored successfully, 0 otherwise. So I'm assuming we call prune in here, or what do we do? Get the minimum register. If we have gotten one, then we color it with that register. We move on and say, so what does this actually do? Web ID. If web ID is less than web index, web next, web ID. Gang gang, I'll smoke to that, King Bun says. Lamau. Ruark says, dude, you have to watch what you're smoking to or you're gonna smoke too much. King Bun says, oh geesh, that sounds tragic. I'll smoke to that. Lamau, King Buns, you get it. Sir, it says the webs are currently a linked list, not a vector. So I can't just index into it. I'll change that later properly. Oh, you're just, okay. Yeah. It's now making sense. This is to convert an index into an actual web. That is totally cool. I'll change that later probably. Don't feel like you need to. Ruark says, no, read again what I said. Dude, you have to watch out what you're smoking too, or you're going to smoke too much. I think I read it as the wrong too. You have to watch out what you're smoking as well, or you're going to smoke too much. Which would be like, I don't think you can smoke too much based on what you're smoking. I mean, you could probably smoke too much heroin, but I'm sure you'd fall asleep before you could physically smoke too much heroin. I'm sure someone could prove me wrong. Don't, please. I'm not telling you to. But I'm pretty sure it would be very difficult, just physically, to actually do it, to get things in the right timing. Like, can I inhale enough before I fall asleep to where I will die? Ruark says, I think I just put too many O's after the T. I always put too many lines on the T. Ends up with 2 lines. Because I write one as I write the letter, and then I go back and cross the T's, and then I'm like, oh, that T has 2 lines now. So we have to spill the web if we can't assign a register to it. Makes sense. And the idea is basically while there's a stack, pop off the stack. Also, vector pop as a macro is very interesting. Ruark says, bruh, I thought you meant a different type of line because of the context. Ha! Lamau. The vector macros are at the top of the file. Ooh, bless. Do vector capacity is less than count plus elements capacity times 2 realloc. Oh, that's beautiful. Append a vector to another. Oh, wow. Okay. Yeah. I'm starting to get it. So basically count refers to how many things are in the vector. Capacity refers to the total size of the vector. That's pretty standard. The vector has elements, which is a number, I'm assuming. And this basically just gives you vector with an amount of elements using realloc. Okay, very cool. What is needs register? Whether an instruction returns a value. Needs register. Oh, okay. Yeah. So we don't need a third register for any of these. Or any, basically, we don't need an extra register because a comment, also we have comments as instructions. A vector has to define data, count, and capacity, basically. Yeah, data is where we store all of our elements. I forgot to mention that part. This is I like it, the simplest vector possible. Here we can start to look at the adjacency matrix stuff. I think King Buns was asking about this earlier. I can't remember. Also, I want to run it. I can't. Hey, it's working. So you can see here's an actual representation of our main function. And you can see that it's assigning R1, aka racks, to everything. So racks get stored in here. Immediate 88 stored in racks. 32 stored in racks. Load of Euclid stored in racks. Call racks with racks and racks as arguments. Ooh. Sir 8 says comments are instructions to make sure they end up in the right place, lol. They're basically metadata. That's really cool. I like that idea. Inserting metadata into the IR. When will y'all realize Rack spits facts? Lamau. But as you can see, we're not quite there yet. Pretty sure that's clear. We're not quite there yet, but we are actually getting somewhere. I would love to print out this adjacency matrix. I don't remember where it is. Probably in IR. Adjacency. No, it's probably here then. Well, this is defined in the type C, so of course it's in here. Where are we at? We build an adjacency to do coalesce registers. I like it. Remove vertex. Also, couldn't this be a to-do macro? That's kind of semantics. It doesn't matter, but... Where is this? Where are we at? There's got to be something at the bottom here. Here it is. Perfect. We found it. Can you comment out? That's crazy. You can use inline comments to comment out multi-line comments. Lol. That's awesome. I don't know why I think that's so funny, but it is. Hey! So if it's greater than rows, then we print what? W blah? Otherwise print blah 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 blah. That's fine. When do we print the numbers? Probably with each of the rows. So R2, or blah blah blah. And then this is where the integers, so instead of saying for rows, we should say j is less than, not the total amount of rows, but the current row we're totally on. Look at that. I think we may need +1. That's a little cleaner. We're going to live with it. We're going to live with it. J is less than or equal to I. That's also a possibility. Same result. Okay, so now we can see with this interference graph, let's try and go figure out what this means. Because as far as I know, an interference graph should be like nodes with edges. So how does this represent nodes with edges? Because that's a graph. A graph is made up of nodes that are connected by edges. This doesn't look like that. And I'm sure it does represent that. I'm just too dumb to figure out how right now. Values interfere. Where are we at? That's just getting the index. I like that. Build webs. Build adjacency matrix? Question mark. So is it going to be in build adjacency matrix? Compute adjacency matrix. So registers always interfere with each other. So basically these are meant to be hardware registers. So R1 through R7 are meant to be racks, RBX, RCX, RDX, etc. These are meant to be actual registers. King Bun says, I googled it and found some pretty nice images. Hey, that's good. Sarade says, yes. So all of these in the these are no longer temporaries. So they look like temporaries here. These aren't temporaries either. We should have a different syntax for printing out actual like hardware registers. I know that's just the debug printout right now, but just in the future, hardware registers in our IR should probably be printed out specifically. Was vreg, but is now I, this is right. I like how the to-do says this is correct. To-do, this is correct. Yeah, percentage R1 is racks. Okay, we're starting to understand it now. King Bun says, I agree, temporaries, and registers should be separated. 100%. I think that should just be a new syntax here. But this is also only happening for debugging right now, so this is not something that needs to happen before it can get merged. It's just something that goes inside our little mental to-do. So registers always interfere with themselves. That's what all these ones refer to. So we can kind of reason that if R1 and R2 both store a value, well, R1 and R2 are racks and RBX, let's say, like two actual hardware registers. You can't actually store those in the same register, can you? I'm pretty sure you cannot. So the solution to that is to say, okay, each register interferes with its every other register. These are all ones. If we were going to draw this, and I'm not, but if we were going to draw this in its entirety, right? Wee, bunch of new lines. Then what we would end up with is like R1. I wonder if I could use artist mode. So, whoa. Hey, look, I closed Emacs on accident. So, also, if you didn't know, Emacs has drawing within it. Deal with it. You probably want to see these. So, what do we got? We have like R1. We have like R2, right? We're going to have R3. We're going to have R4. And the thing is that each of these things is actually going to get its own connection because each of these ones refer to an edge in a graph. So if I actually switch to text, R1. Oh, Figlet is not. I tried to use Figlet to create the text. Did you see that? Figlet is not recognized. Lol. Okay. In any case, we can just switch out of artist mode and type R1 and R2. So these are hardware registers, let's say, right? I know this is a terrible graph. Bear with me, please. So we're going to draw with our pen. And you could imagine that R3 and R4 have a 1 there, R3 and R4. There's a 1 here. So these interfere, which means they'll be connected by an edge in our interference graph. And also R3 and R2 and R1 and R2, and also R1 and R3, and also R2 and R4, right? Where are we at now? So R1's connected to R2, R1's connected to R3, R1 also has to be connected to R4, right? R3 is connected to R2 and R4, but it also has to be connected to R1, which it is. R2 has 1, 2, 3, 2. Soraid says the actual interference graph that the register allocator uses is adjacency lists. By the way, the matrix is used to build lists. Also, conceptually, this is exactly right, but the implementation is a bit different. Exactly. This is the math behind the implementation, right? This is the actual math. Like if you were going to tell a mathematician about it, you'd say, okay, there's 4 nodes or 7 nodes, and each of them are connected to each other because they all interfere. And each edge represents an interference. This would be the graph, but our actual implementation is not implemented in computer science as a graph. It's implemented as something entirely differently called adjacency lists, as just mentioned. And if we take a look, I think it'll make a lot of sense. An adjacency list is basically just a color, a spill offset cost. So this is just spill stuff. We don't got to worry about it. Interferences, which is a size t. That's kind of interesting. I don't know how that works. Sir Aid says pretty much. Perfect. And then we have a register vector of interferences list. See that? Oh, so this is just amount of interferences. That starts to make sense. Well, this has count. Why do we... Okay. Interferences is the number of edges, basically. Ah, I see. I get you now. I get you now. Yeah, then a node stack and an inner. Yes, yes. This is starting to make sense. So we have a bunch of adjacency lists with a matrix and a stack. And I'm assuming the graph is basically just using this matrix to create the lists. And eventually, as we can then fill up the stack and then pop from the stack to slowly color the graph. Cool. Anyway, so you can imagine each of these registers are going to be connected to all of each other because they interfere, and effectively the graph we're building, each node within it, if it is connected by an edge to another node, cannot and must not be stored in the same register. Does that make sense? I think that's starting to make sense. Okay, so we have our webs. I know this is a jump. What is a web interference? If any one of the temporaries within A interferes with any one of the temporaries within B. Big jump there, but bear with me. So then we find nodes that don't have edges to other nodes and make our list of registers based on that. Close! You're very close. So we take a look at these webs, right? So these webs, we don't print them out. Let's see if we can figure out where that went. Assign registers to the webs to do spill values. So here's the print webs thing. So let's print out all of our webs. And as you can see, our webs refer to lists of temporaries, right? So all of these must be stored in the same register. And I'm sure we could make more sense about this. We did this. Okay. So you can see now, when we're not using hardware registers, we're saying that our virtual temporaries start at R8. So imagine just all of these are temporaries, except for R1, right? So you can see that in main, we start out with our temporary of a function. We store the temporary into a variable, a global variable. And we have all these new temporaries. Starts to look a lot like what we wrote earlier, right? So from this, we can create these webs. So you can tell that R11, stored in R11, it lives and dies right here. So it doesn't interfere with much, but it also doesn't have a phi or copy node related to it, so it's really not important. So it says also, depending on how we implement coalescing, we might be able to just reduce phis to copies and get rid of webs entirely and just use values directly and let the coalescer handle the rest, but we'll see. True, I think that would make less efficient code. Oh, it wouldn't, because then the yeah, you're correct. We could probably get rid of phi nodes. That'd be cool to be able to not have phi nodes in our IR, because then people wouldn't have to understand them. Because the thing is, a lot of the work that goes into building webs is already done because the IR is in SSA form. Exactly, that's what I was just thinking. Like with SSA, the webs kind of refer to only things that are copied. That's why I keep saying that SSA is great. Again, I wouldn't say SSA is great. SSA is just a way to do things. I think there are better other ways to do things. But it may include SSA. I don't think they're mutually exclusive. So SSA is good. It's a positive thing, but I don't think it's the best thing. You could argue that that's what great means as well. So with this, we can see that R11 has no phis, no copies, so it's just in its own web. R10, same thing. R9, same thing. When it comes to the actual return value, however, you can see that we're actually calling this function, this GCD Euclid function, after defining it, right? So we call this function, and then we branch to our return. So this temporary that is meant to be the last temporary in the basic block, this is meant to be the return value of this basic block. So this return value of this basic block, R12, must be stored in the return value of the function when we branch to the return block, which is always the first block within a function, which will return. If this is making sense, that's good. So R12 is the result of this call, and that's what we want to return, given we return right away. This is needed because there may be another control flow which also branches to BB0 but sets a different result value. So those temporaries must be stored in the same thing. And then R13, our return value must be stored in racks. So that's why this little R1 equals copy R13 here. So you can imagine our webs, we can now say R1, well here's a copy R13. Remember our web rules, R1 and R13 are now in the same web. And they are. And then R12 is a phi argument of R13. So R13 is a phi, and R12 is an argument of R13, which means that, once again, it merges into the web. So the web 5 of R13, R12, and R1 all get stored in the same web, which means they all get stored in the same register, which means that when we color in the graph, this does contain a hardware register, so this just means that this is the hardware register that we'll store it in, racks. So all of these temporary values can be stored in racks. That's just a real-world example with our actual program that's working. How cool is that? Then, before we can color, right, we have to figure out what webs interfere with each other. And that's like what we did earlier with having all the webs, merging all the lifetimes and then seeing where they interfere. So for example, web 2 interferes with web 1. So R10 is here, and its latest use is here. So that's our little live range of R10. And it says web 2 interferes with web 1, which contains R11. R11, as you can see, its definition is within or in between the definition and latest use of R10. So the live range of R10 is said to include or overlap with the live range of R11, because R11 goes here, R10 goes here. You can see that they overlap. Effectively, what this means is that they can't be stored in the same register. So the fact that web 2 interferes with web 1 means that web 1 and web 2, right? So web 1, according to web 2, must be stored in different registers. Suraid says also, I think we can just store the interfering registers as a bit mask in the adjacency lists and get rid of them in the matrix. That would make a lot more sense because they're always 1. So I don't think they're needed in this matrix. And that would actually make this matrix much smaller, which is pretty dope. Suraid, that's a great idea. Because, so you're saying basically each web, this may be incorrect. Oh, basically each adjacency list would contain a bit mask of the registers with using the same reg mask T. That's a great idea. That's a great idea. Because the idea is that, we're not looking at it here, but the idea is that when there's a divide or something, right? Let's think about this. So when there's a divide or something, let's say 16 over 4, and we'll just say a is an integer equal to it. Why not? This may break things. It doesn't. How beautiful. So you can see that this divide, effectively, divide must be stored in racks. We'll see if this works now, by the way. Still not quite there. Because it should interfere with RDX. Doesn't matter. Don't worry about it. Also, I just did Control W again, and it just yeeted the Twitch tab. RIP. No. Especially since the matrix is O of n squared in terms of memory. Yeah, its space complexity is definitely not the best. It's worse than its time complexity, for sure. But with this division, basically, the issue should be that div will overwrite racks and RDX. So the fact that we use racks and RDX, right, as registers for temporary values, we want to be able to color the graph with these registers. It means that we have to do some specific handling of divide and stuff. But it also means that this web that contains divide, so R11, wherever it is, R11, web 4, should probably interfere with a register RDX, because we want the answer which is in racks. Hopefully that makes any amount of sense. But yeah, that's where we're at. That is where we're at. This is looking really good. So you can see that we're obviously not allocating registers properly. We're not doing the coloring in the right way. But we are actually generating IR that makes some amount of sense, and I'm starting to understand it, which means I'm going to be able to start working on it more and more. How beautiful is that? What is web interference? Two webs, A and B, are said to interfere if any of the temporaries within A interferes with any of the temporaries within B. When two webs interfere, they, I think again, must not be stored in the same register. I think that's valid. I think that's a valid statement. I would say that's true. So King Buns says, I gotta jump on a work call for a little. Will you push that text before you end? Absolutely, King Buns. Sir Aid says, also mentally, I can't read. Also mentally, it's much less jarring to work on something that you actually understand. Exactly. Exactly. It's not like, why, how, what? No, it's more like, oh, okay, yeah, I get it. Yeah, oh, that's confusing, but it makes sense. You know what I mean? It's a little bit of it's a step up. Sir Aid says, because now working on this doesn't feel stressful at all anymore, lol. Sir Aid has enlightened. He has reached the peak level of enlightenment. Wait, can we do this? We're gonna do it. Can we... I don't even know where to do this from. I'm pretty sure this is a good one. Ooh, yee. Wait, are you ready? This is when you do like... Okay, we gotta add text. Also, why is there only top text and bottom text? Shouldn't there be all of them? The fuck? Lol. Okay, we're not doing it. This is Sir Aid. Sir Aid has reached Giga Chad levels. Sir Aid says, oh, that's cursed, Lamau. Yeah, this is an awful website. Don't look at it. But Sir Aid has reached insane levels. He is out of this world. Chaitin-Briggs register allocation isn't even stressful anymore, lol. Gigahead. That's right. Okay. Sir Aid says, or King Bun says, yeah, you don't feel like you are walking on glass when programming. Exactly. Sir Aid says, and I also have an idea of how to design this in a way that's at least somewhat better than just, it works. Well, that'd be great. That'd be awesome. That'd be very awesome. Why are you mad? I can't find the file. Well, you're wrong, because I'm in it. I'm within the file. Like, what am I supposed to do? Alright, there we go. Saraid says that's pretty accurate. Talking about in response to King Bun's walking on glass. Okay. These webs show, that's not ideal language. These webs show that there are no temporaries that must be stored in the same register. I don't think that's ideal. These webs each contain a list of temporaries that must be stored in the same register. Keep in mind that these webs and corresponding temporaries may still be stored in the same register if they do not interfere, calculated later. What is web interference? Two webs A and B are said to interfere if any one of the temporaries within A interferes with any of the temporaries within B. When two webs interfere, they must not be stored in the same register. I think that makes sense. So if we took a look at our little example here, you can see that web 1 and web 2 interfere because web 1 contains R14, and web 2 contains R13. So the fact is, R14 lies within the live range of R13. The definition of R14 lies within the live range of R13. This means that they interfere. And this means that they must not be stored in the same register. So web 1 and web 2 each may be colored with their own unique color. Another way to say this is that web 1 and web 2 are connected with an edge in our graph. And remember, edges within our graph refer to interferences between webs or values. Again, we're moving away from webs towards just having values or IR instructions, which I think is a better term. Instructions. Because each of these is truthfully an instruction. Or we should call them temporaries. We'll get there. Anyway, so we calculate whether these webs interfere with each other, store it in this little bitmask matrix, this little beautiful thing here. And all we have to do then, as you can imagine, is color in our actual webs. So with our list of webs, we then will contain our list of edges, right? So our interferences. So interference between web 1, web 2, web 1, web 3, web 1, web 7. So web 1 would be a node. Scratch node. Right? And the idea is that web 1 would be a thing, and it would be connected to web 2, web 3, and web 7. And the confusing part is then we do this for each one, right? So web 2 is connected to what? Web 3. Well, technically web 2 we already know. It's connected to all of these through edges, right? So web 2 is connected to web 3, web 7, and web 1, is it not? 3, 7, and 1 would be there. Yes. So effectively what we have is more like W1, W2, W3, W7. Then, so what's W4 connected to? Because that's not connected to any of those. So W4, web 4, is connected to 5, 7, and 8. See, here's the graphness coming out. See, this 7 is connected here, so 4 would be connected. Ooh, beautiful. By the way, do we want to move the vector macros into a separate header? Because I feel like we might want to use them somewhere else too. I'd also call it vector.h, just to mess with C++ programmers, lol. You can move them into their own header, as long as we don't call them vector.h for, I'm sure MSVC would complain about that, because it's a C and C++ compiler. It doesn't really know the difference. Okay, so effectively, using this interference matrix, we can draw edges between nodes, which Emacs is not the best at. Plain text, turns out, not the best format for that. I guess I could just do this. The C++ header is vector, no.h. We can call it vector.h then. If it doesn't make, if there's no problems, why not? Let's screw with them, right? Okay. This might be bright. Just, I gave you your warning. This might be bright. Perfect. We've done it. Okay, so effectively, oh, I'm on the wrong screen. Oh God. Okay, is that correct? Nope, that's across both. There we go. So effectively, what are we looking at? We're looking at this matrix, and as you can see, also you can't see my mouse very well right now. As you can see, we're looking at this bottom right triangle here, because this is where webs interfere with webs. So let's start with web 1. Web 1. You get to see my awful handwriting now. Web 1, which is connected to web 2. So these would be both... Ooh, I cannot draw. I'm a programmer, I'm not an artist. W1 is also connected to W3. How beautiful is this? W2 is also connected to W3. Just so you know, that's why that goes there. So W1 connected to also W7. Okay. Also, I should probably like do this. Oh God, no. What have I done? Don't go 3D. Don't undo. Just please move view back to orthographic. Blender Y. Blender Y. There we go. Shift drag. So why is the camera now visible? I don't want to see the damn camera. Damn it, Blender. What you doing? Okay, so with W7, whoops. W7. W2 is connected to W3 and W7. Look at that. So W2 is connected to W7. Isn't that fun? W3 is connected to W7. Would you look at that? W7's a popular boy. Interferes with everybody. W4 interferes with W5 and W7. So we're going to have W4 now. And then we're going to have W5 connected to that. So W4 connected to W4 connected to 5, 7, and 8. Look at this horrible handwriting. We're starting to build our graph, right? And then also there's no guarantee that this is correct. So we did 4. W5 is connected to 7 and 8. So W5 is connected to 7 and 8. W6 is connected to W7. And W7 is connected to W8. Boom. Here, we'll do like that. What a node. What a graph, right? So it looks like W7 is in the center, at least to me. Then we have like a branch off to W4, which goes in line with W8. So these get it connected. These get connected, right? We get a little triangle here. And then we get W5, which has to be like way out here because it's connected to both 8, 4, and 7. Is this starting to make any amount of sense to anybody, by the way? Then we have W1, W2, which are connected to each other, and W3, which are all connected to each other. And then 2, 1, and 3, so all of these are connected to 7. How beautiful. And then there's 6. Web 6 just hanging out. So with this, why is this important? Why do we even need this? Right? Well, we need this because also I should probably erase some stuff. Oh no, 100% strength, please. Yes, goodbye. Goodbye and good night. Okay, how perfect. We're done. So with this little interference graph between our webs, right? How do we color it such that no two nodes connected by edges are colored with the same colors? There's a lot of ways to do this, right? And this is literally the register allocation part, because when we're talking about colors, just switch out the word color with register and everything falls into place. So the idea, also I'm going to have to make a note of this, a diagram of this in LaTeX, and this is going to kill me. But effectively, with this little structure here, which is from our real program, right? So this is an actual graph that will happen in a real program. We have to have some way to color it. And luckily, there's these ways called the Chaitin-Briggs algorithm, or Chaitin algorithm, right? Uses coalescing and biased coloring, blah, blah, blah. Effectively, the idea is, where are we at? Coloring. Yep. Graph coloring register. Okay, so there are different ways to do it. And the main idea, this doesn't specify it very properly. Let's see about that one that King Buns recommended. Hey, perfect. So these are the webs that we're talking about, by the way. This is how they can be represented. Sorade says, also, I just made vectors much nicer to use. Hey, that's Pog. Coloring for n is greater than 2 is NP complete. So effectively, a node with degree less than n, by the way, the degree of a node is just how many neighbors it has. So the degree of W7 would be 1, 2, 3, 4, 5. Does that make sense? Can always color it successfully given its neighbors' colors. A node with degree less than n can always color it successfully given its neighbors' colors. So what this means is that if degree, so if you have like n registers, so let's say we want to have n registers, it can always color it successfully if the degree is less than n. So the fact that W7 has 1, 2, 3, 4, 5, 6, 7, also 7 connections, then this means that there must be a solution. There must be a solution, it is proven, where 8 colors can color this graph. There may be ones with less, but if the degree is less than n, then that means that n amount of colors can color the graph. So the other way to say that is that a graph, given the maximum degree of any node within the graph, can be colored with the maximum degree of any node in the graph plus 1 colors. There's some comments in prune interference graph that explain this too. Oh, beautiful. We'll check them out. We'll do here. What is probably ra.c prune interference graph. Okay, here it is. Look at us. Apply the degree is less than k rule. A graph is k colorable if, and only if, for every vertex, not and only if, I'm just messing with you, in G, which is the graph. So for every vertex in our graph, for every node, the degree of the vertex, the degree of the node is less than k. Basically saying, k, if every vertex has a degree less than k, you can use k amount of colors and it'll work out. So any node that has less than k number of degree, right? It's number of neighbors. Then what this means is we can just push it onto the stack. So what this refers to is going through this and saying, okay, also I'm going to save this really quick. Don't pay attention to shitty things I've made. This is going to be like node. So this is going to be interference graph theory. Perfect. And effectively, what we're saying is that, can I make a new thing here? Yes. What we're saying, I keep saying that. So let's figure out the degree. So W7, you could get the degree of this node, and it would equal to the amount of neighbors it has. It has 1, 2, 3, 4, 5, 6, 7 neighbors. So that means this graph, if this graph is called G, right, then that means that G can be colored, can be colored with 8 colors. How beautiful, right? So G can be colored with 8 colors because the degree of the node, the vertex with 8 colors, right? The vertex with 7th degree, that's the highest degree of any vertex in here. So we know that this entire graph, the maximum degree is 7, so G can be colored with 8 colors. So W7 is max degree, is what we'll add there. So with W7 having the max degree, that means G can be colored with 8 colors. At most 8 colors. It's possible you could color it with less, but we know mathematically it's proven it can be done with 8 colors. Ain't that cool? And it may be at least 8 colors, I'm not certain. Also, as to why it's pushed onto the stack, I'll add another comment addressing that. That's cool, that's cool. I was going to go into that as well. Basically, but that's a good idea to have that in the code as well. So what is this little rule he's talking about? Apply the degree is less than k rule. So the interesting thing about a graph is that you can remove nodes from it, and it doesn't change the rest of the nodes. The only thing that changes are the edges that connect to that node, right? So all you have to do, and also k here, k refers to our number of registers. So k, which is our number of registers, hardware registers, is the degree must be less than k. So this k can also be thought of as number of colors, number of registers, etc. Whatever you're coloring in the graph with. And effectively what we do is say any node, start on any node. And if it has a degree of less than whatever you're getting, then go for it. So what we're going to do, right, we're going to make a new layer. We're going to say, okay, so let's just pick any node. It said any node. Let's just pick W1 because that sounds fancy, right? So the degree is equal to what? 1, 2, 3. It's connected to 3 things. Let's say that we have a k. Also, this is kind of in the corner, but deal with it. Let's say we have a k of 7. Let's go with something simpler. Let's go 10. Right? So we have 10 colors that we can color in this graph with. Maximum. So this would be like our amount of registers, hardware registers, or anything. So W1, the degree is equal to 3. 3 is less than k, which means, what do? We know it can be colored, so we remove it from the graph and push it onto the stack. So this is the complicated part. You then remove W1 and then push W1. Right? And then our stack contains at the bottom W1. So we'll put the bottom at the top. It's fine. Mr. Mugame says, why are you drawing in Blender? Because I can't draw like this in Emacs. That's it. So we push it onto the stack to be dealt with later. And then we remove it. So effectively we say, okay, done, removed, which means this edge no longer exists, and this edge no longer exists, right? So this is gone, this is gone. How beautiful is that? How beautiful is that? So W1 can then be removed after we push it onto the stack because we know it can be colored. And then you just take this resulting graph, which you could call G prime or whatever you would like to call it, and you do the same thing. And let's pick W2. The degree is equal to 1, 2. There's now only 2 connections because this edge has been removed. So degree is equal to 2. 2 is less than k. Remove. Push. W2. Right? Continue on. Say, okay, no more W2. Now let's go for W3. How beautiful is this? Degree is now 1. 1 is less than K. Remove push. How beautiful is this? Dot, 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 dot. And then we would remove it. Now, you may be wondering, what happens if degree is not less than K? And in that situation, you know what we do? We do a big ol' to-do, right? We don't actually do any spilling currently. So what happens when we don't have this enough K, right? If K is too small and degree is too large for K, it's equal or greater, then what we have to do is what's called spilling, which is basically creating a new interference graph after removing the node that isn't able to be colored. The second big comment explains what happens if the degree is too big. Perfect. Apply the degree is greater than equal to K rule. Exactly. At this point, the graph is either empty or contains only vertices with degree greater than or equal to K. Because we pick any node which has a degree less than K, we'll go through all of them eventually. And let's say K was 6, right? If K was 6, then we would go through all of them. W8 degree less than 6, W4 degree less than 6. All of them are less than 6 except for W7. And this is what we would be left with in this case, a graph with just W7 in it connected to a bunch of things. But here's the interesting thing. W7, if you don't start on it and you start on something with less, it'll actually end up with less degree than K because you remove you remove the edges. So W7, even though it starts out as having 1, 2, 3, 4, 5, 6, 7 connections, it turns out when you actually go to color it, it only has 4 connections. Does that make sense? If we picked it next, or we could pick something else next, and then get back to this, and then it has less edges, and guess what? We can now color it. Isn't that beautiful? So we can just slowly color this graph until it becomes its own thing. Also, we haven't talked about what the stack does, but we'll get there. Basically, Chaitin's algorithm would spill here, but we can do better, as Sir Ade says. So our normal algorithm would say, if the degree is greater than or equal to K, we're screwed. Sir Ade says, and no, we don't have to spill. You're correct. There are ways to avoid it. But if we go through every node with less than K and remove it, then ideally we'll end up with nodes with a degree less than K. If at that point even we don't end up with nodes less than degree K, that's when this has to be implemented. This basically never happens. Okay? It's in the real world. It's like most of the time you can just store everything in registers and it's fine. There's complicated situations, obviously, but most of the time you can just store literally everything in a register. Isn't that beautiful? Isn't that beautiful? And that's how register allocation works. In any case, Briggs, so the Chaitin has an algorithm. I'm going to say this as Chaitin, by the way. I don't know how to say this. It could be Chaitin, it could be Chitin, it could be Cherble. I don't know. But Briggs's improvement to Chaitin's algorithm is to select the vertex with the lowest spill cost, which is some heuristic, some calculation you make to say, how good is it to spill? But instead of spilling it, it too is pushed onto the stack. You're pronouncing Chaitin correctly, lol. Yay. It's a weird word. So effectively, you can take one and push it on the stack and color it. This works because a graph G is K colorable if, not if, for every vertex V in G, degree V is less than K. What does that mean? For every node in the graph, the degree of the node is less than K. This means if for every vertex, because a graph G is K colorable if for every vertex in G, the degree is less than k. This means that even if there is a vertex V in G with degree greater than or equal to k, there may still be a k coloring of G. Because it is not if and only if, it's just a proven statement. It's not the only way to get the answer. So spilling may not be necessary, but we don't have enough information yet to determine that at this point, so we optimistically push the vertex onto the stack and defer spilling as much as possible. Basically the same thing that we said before, but emphasizing that it's if, not if. Exactly, that's what I was just realizing. This isn't the only answer. A graph G is k-colorable if this is true, but a graph G may also be k-colorable if something else is true. A classic example of this is the graph below, which is 2-colorable, but Chaitin's algorithm would spill a vertex. So A, B, C, and D all being connected, the algorithm would go through and say, yeah, so if k is equal to 2, it would say, oh, this is actually equal to 2, we have to spill 1. So the first vertex that you choose, whatever it may be, it would say the degree is greater, so it won't work. But as soon as you remove it, then the degree is 1 of all of them, in which case you can just color the rest of them in. Rather than spilling, which, by the way, spilling in a literal sense means storing a register's value on the stack so that you can load from it later. And it means you don't need to keep that register allocated. Suraid says, it's a sufficient but not a necessary condition. That's a beautiful way to say that, Suraid. Talking about the if and not only if. So this graph is 2-colorable, but Chaitin would say it's not 2-colorable. You actually need 3 because of the beginning node would always have a degree of 2. And because the less than or equal to k is Chaitin's algorithm right here, that's our little issue, right? So the issue with this new, this Chaitin's algorithm is that we'd end up with a spilled node even when we don't need one. So if it's greater than or equal to k, Briggs said, hey, most of the time Chaitin just gets it wrong. What if we just pushed it anyway? What if we just push it on the stack anyway, based on the one with the lowest spill cost, which in this case would be any of them, right? So this determines the node with the minimal spill cost, and then it spills it. It doesn't spill it, it just, you know, puts it on the thing. But it would be the node that we would spill if Chaitin's algorithm was followed. But we try not to spill it very hard. We may, but we may not. Effectively, after we do that, we have an interference graph. Well, we have some stack, right? Interference graph. So after this, our web assign registers to the webs. Perfect. So now we can look at assign registers, which is broken. It's pronounced Chaitin if you know IPA. I was wrong. The AI in Chaitin is pronounced like the I in Phi. Nice. So it's Chaitin. Chaitin, not Chaitin. Oh yeah, the AI in IPA. International Phonetic Alphabet, baby. So then, once we have this stack of colorable nodes, all we have to do is for every vertex that we pop off of the stack, which is WI apparently, then we try and get the minimum register based on that index, which effectively return the smallest register that can be assigned to the vertex at the given index. Return 0. Yeah. Coolness. So the register mask is a bit set where each bit represents a register. If the bit is set, then the register is in use. How beautiful. For I is less than interferences list dot count. So for all of the interferences, given a graph G, lists data index list count. So for every interference adjacency list, right, effectively, create a register based on how it has been colored. Do you see that right there? So we use the color, which I don't remember ever being set. I don't remember .color ever being set. Oh, it's set right here in assign registers. Okay, that makes me feel better. But min register is called first, before the color is set to the register. Oh, but that's different. That's data at WI of lists. G lists data index. Interferences list. So this is the interferences color. How beautiful is that? So we basically say the reg mask is set based on the color of the interference. So is this stuff that doesn't interfere? I'm confused here a little bit, but I'm sure it's just me. I'm sure it's actually at least correct. Then we look for removed interferences and assign registers there. So this has to do with the adjacency lists that I'm not quite understanding. So how does an adjacency list represent a graph? So an adjacency list has a color, spill offset, a spill cost, interferences list, removed interferences list. I'm not smart enough to make this connection yet. My brain is trying and I'm like, wait, what? My thing is gone. Basically, each adjacency list by Sir Aid says this. Each adjacency list corresponds to a vertex. Oh God, what have I done? There we go. Corresponds to a vertex and contains the vertices that are adjacent to it. Oh. Oh. Yeah. Thanks, Sir Aid. That was an amazing explanation, by the way. What he's saying is that each of these webs was a vertex. By the way, we keep switching between vertex and node. I'm going to go with node from now on. Each node within the graph, right, we essentially assign an adjacency list to it. So, right, we're basically going to have what? We're going to say W1, oh, it's red. Black, please. Also, I'm using my mouse now, so it's going to be straight lines. W1 effectively gets a list, and it contains an adjacency list. Okay, this is starting to make sense. So this is a list of edges. So W1 has W2, W3, and W7. W3. So we'll just make it a Lisp list. W3 and W7. W2 as W1, right? And it's not going to be complicated. W3 and W7. W3 contains W1, W2, and W7. W4 is, there's a lot, 7, we got 5, 7, and 8, right? So if we just switch to numbers, this will be a little faster. And then you can see W5 has 4, 7, and 8. How beautiful. And we will go over why this is better when we go to actually color the graph, because it does make a lot of sense. And then 7 should be our last. Well, there's still W8. So 7 is connected to 1, 2, 3, 4, 5, 6, and 8. 1, 2, 3, 4, 5, 6, and 8. Ooh. And then W8 is connected to W4, 5, and 7. Okay, these are adjacency lists, right? This is better. I understand this a lot. This is better because when we're actually, where is it? Pruning interference, assigning registers. Perfect. So what we're saying is pop a vertex from the stack and assign it a register. So we try and get a register for some vertex on the stack. So imagining this, remember our stack had like W1, W2, W3, etc. So imagining that we end up with W7 as the end, then we say if we get this, get the web based on its integer, its index within the linked list, and assign the register to each value in the web. Because remember, each value in a web, each IR instruction, should actually be stored in the same hardware register. So when we allocate a register for one, we allocate a register for all. Pretty beautiful? If we couldn't assign a register, then we have to spill the web. Yeah, we're not there yet. We don't do that. And we almost never will need to do that because of how beautiful this algorithm is, right? So you see the stack basically just gets you something to color. And then once you color it, you assign it to all the values in the web in the stack, which again, we may move away from webs and towards just having values, just having temporaries that are assigned with copies and stuff. We will see, we will see. And you'll notice that these adjacency lists here, if we actually go back to, where was it? Where were we? Oh God. It was min register. So basically, interferences list is a register vector in adjacency list. So this is an adjacency list. So when we're looping over adjacency lists, we're actually looping over every single node one time in the graph. That's actually what that means. Okay. So for every node in the graph, the register is however it has been colored based on the adjacency list's color. What does this mean? What does this mean? So where does this get colored? So this is saying like, oh, W2, right? So we're looping over every value in the adjacency list. Is this proper? Interferences list. So this goes through all the interferences. Sorade says yes. Okay, so this goes through all of the interferences and says register is color, register is in use. And then we say removed interferences. I'm not sure where this comes from, but I'm sure it makes a lot of sense. And we say that color is also in use. Because as we go through, remember that we remove from the graph. So we may have interferences that are actually removed from the graph, but that's they also have to be stored, if I'm correct. That's why we need two loops here. To find the smallest register that can be assigned, we simply find the first bit that is not set in the register mask. Oh, now it all makes sense. Oh, I just had to read all the way to the end. So the reason we create this register mask, we basically go through all of these interferences. So let's say we have like registers, a bunch of registers, right? We're going to start with 0. What did I just undo? Yeah, we're going to start with 0. So we're going to have like 0, 0, 0, 0, 0, etc. This is starting to make so much sense, Sir Aid. Reading my comments all the way to the end usually helps. It's true, I just didn't realize this was, basically, I should have figured out where is the register mask actually used. Because in my brain, this was a global, but I wasn't paying attention. This is a local that's reset every time. And now it makes so much more sense. So in W1, right, we would go through and start with our, can you hear me losing my voice? We would go through and start with our register mask, right? Oh God, I'm sorry. I can't type, I can't write with a mouse. Mask, oh God, no. Mask. Good enough. Starts at 0, right? But then we'll go through and say, okay, for W2, W2 was colored already, or it wasn't, right? And if W2 wasn't colored already, then that means its color will be 0. And when you bit shift 1 by 0, guess what happens? Oh wait, when you bit shift 1 to the left by -1, is that what's happening? That is what's happening because it's an integer. So we bit shift 1 to the left by -1, which means bit shift it to the right 1, which means 0. And if you AND it with 0, you know what you end up with? 0. How beautiful is that? So if this hasn't been set yet, also, there's some curiosities there. We may want to have like a check if this is 0 and then update reg mask, because if we actually have one later in the list that results to 0, it'll clear out all the previous ones. Something to think about. Just because of that register -1. Yeah, we should probably check for that, lol. Hey, Sir 8 agreed with me. I'm actually beginning to, I'm giga chatting, I'm giga heading chat. It's working, I'm giga brain. Sir 8 has pulled me up to his level. Also, my internet's crashing. Please don't lose the stream. Oh God. My bitrate went down. It now tells me I have 0 viewers. Are you still here? But effectively, for W2, it hasn't been colored yet, so nothing happens. W3 hasn't been colored yet, set to 0. Hasn't been colored yet, set to 0. So guess what? Our register mask is 0, so finding the first bit that isn't set in, nice, find the first that is set in not mask. Finding the first that isn't set in the mask means that we can just return that register. If first set is greater than numreg 0. That's fine. Otherwise, we get the actual bit that is set within the mask. How beautiful, how beautiful. So what this means is W1 will say, okay, what's the first that's not set? And then it would go, check out find first set. Okay. Oh no. No. Why would you do this? No. The conditional compilation. Find first set long long. That only works if this is a long long. This will only work on 64-bit systems. So we should check for Win64 like this. Just so you know. This is beautiful though. So we're using compiler built-ins, which is what these underscores mean. If it starts with an underscore, you can guarantee it's a built-in. What is this a built-in of? Is this a GCC extension? Is this a GNU extension? What is this? Also, does it find first from the left or first from the right? Also, this doesn't find it in a word. That would be in a quad word. Not that that's important. Clang should support it too. Clang should support GNU extensions. Yeah, it's a GCC extension. Sweet. If we're on Apple, we have some things to deal with. I mean, I guess Apple either uses GCC or Clang, so we should be good there. Okay, yeah, this should work. This should work. That shouldn't be word, rip. You know you have it good when your pull request has comments like, this says word and not quad word in a comment. It's like, you know you're doing it right. That's very cool. But yeah, so we find the first set within mask, and then basically, if it's greater than the number of registers, then we say, hey, this should have been spilled and this is a big deal. Just return 0. This should never actually happen, because we should have already spilled everything before assigning registers. But that's not important right now. What is important is that effectively we can get a register based on if they have all been set or not. So W1, the mask is 0. So the first set is just going to return none, right? Find first set is going to return 0. So we're basically just going to return 0. Is that true? Because there's no, if this is our bit mask, I know it's not 64 bits, but if this is our bit mask, would the first one not being set, does that mean we return 0? Versus this would be bit 1, 2, 3, 4, 5, 6, 7. How does the actual case, the 0 case get handled? You know what I mean? Oh, find first set in not mask. Hey, Serraid says 1, not 0, I think. It depends on how you count it. You're correct, though. It's because we're finding the first that's set in not mask. So effectively, these would all be converted into 1s because they're knotted, right? They're put through a NOT gate. And then the first one that's set would be here. Beautiful. Okay, so then we find the first one that's not set, which would be this one, and then we just return 1. First not set. Oh god. Yep, an E. Oh god. Return bit index. So if you don't know, bits are indexed on most systems from right to left because they have a specific endianness. Return bit index. Oof. That's a big E and a big X. Lol. So this would return 1. Right? So this would return 1. And what this means is that register is equal to 1. If 1, yes, color equals 1. Look at that. And then all the ones in the web. There's none in this web. We're not dealing with values at this moment. We're just thinking about webs. Okay? So then, when we go to do web 2, our mask that gets built will start again at 0. But here's the thing. Now, when we loop over its interferences, one of them is W1. Its color is no longer 0, which means, guess what? It gets set. Also, that's Sir Abe. This is why everything's being assigned to racks. I just figured it out. You're welcome. I just realized what I told you earlier, that bug of checking for whether this is 0 or not. That's actually our problem. Pog, it could be working now. Hey. So effectively, we set this mask and say, this should be OR equals, right? That's our issue? This should be OR equals? Yeah, it should be OR equals rip. This would work, though. That's cool. I wouldn't say that's a rip. That's a good problem to have. You know how many times in Lenser OS I did an AND instead of an OR? It made me want to die every time, too. So with our mask, not mash, our mask, it would then be set to the color of W1. Because look, that's one of our interferences in our interferences list. Look at that. So now, it returned 1 last time, right? So our color would be 1, which means that all we have to do is say this bit would be set. And then finding the first not set would be womp here. First not set. Index 2. Then we can go to W3. Now it has W1, W2, which has already been colored, and W7, which hasn't been colored, so all of these will just be 0. Which means the first not set, again, will be here, and this will be index 3. Isn't that beautiful? Then when we get to 4, guess what? The mask will be set back to 0 because none of these have been colored yet. So when we get, oh god, no. Oh god, no. Please keep my math 2D. W4 would end up with 0, 0, 0, 0, 0, 0, 0, and 0, which means we would return, again, index 1. And these indices then can be mapped to registers. Ooh, Pog. Do you see how this works now? We just spent like 4 hours going over it, so I hope it starts to click, but man, do you see? We can now allocate registers for every single value within the program using this technique. Sir Aid says, damn it, I could write a really nice vector for each if it weren't for the fact that MSVC doesn't support __ type of __. Can you really not get the type of something in MSVC? That would be so ass. I'm sure you're correct. Hey, look. Yeah, it's easy. Easy stuff. No, we got to figure out. You can use _generic on it if we use the new C standard. That's actually useful. RIP. If you're compiling in C++ mode, which we often are, you can take advantage of decal type. So if def C++, we can use decal type, like this. Otherwise, we can use type of. This is why I never support MSVC. This and VA opt. Lamau, you write too many macros then. Because it's literally, it's doable with decal type if in C++. So we'll basically say, if not C++ and MSVC, just literally do a hash error, do a preprocessor error, right? Because we can just say, we don't support this type of platform. You have to compile with C++ if you're going to use MSVC. I think that's totally fine with me. Because MSVC doesn't have like C and C++, it's just a literal command line flag, so this is just solved by a command line flag. We can totally error and do that. Sir Aid says, thanks. Of course. I know I've done this before. I've done a type of macro when I was doing this language called E that I worked on like a year ago. I didn't get anywhere with it, but I loved designing the language of E. It looked a lot like our current language, hint, hint, nudge, nudge. But basically, I remember using type of, and I was having the same issue on Visual Studio. But decal type works most of the time. Again, _generic we could probably also use with newer versions, but that's a new thing. I don't think that was, what is that? That's in C11, which should probably be in C++, yeah. Interesting. Perfect. Yeah, so _generic lets you do this syntax. You get to decide on the type of X what you would like to do. I'd recommend C11 anyway because static assert. Yeah, we should probably do that. I think we can do that easily in CMake, if I remember correctly. Also, oh my. What does coloring accomplish? Well, that's literally register allocation. Phi, yes. LenderOS got a pull request. That was so awesome. Thank you so much, Lander. I don't know if you're still here, but this is just, I love seeing work on LenderOS get done. I wish I had more time in my life, because it just takes so much time to get into the OS. And I want to work on user space processes like a window manager, but whoa, I'm broken. I'm broken right now. Sir Aid says, I can add that to my IR branch as well. Oh yeah, something that has to be fixed in your IR branch. It's not a big deal. I do the same thing all the time. We can't actually include these compile options. Again, this may have been me that coded this. I don't remember. But we can't actually include these because they don't work on MSVC. These require commented out. we'd have to use a generator expressions like if GNU, which I don't even know how to do. We'd have to do like CC, and whether that is equal to, oh god, yeah, it would be rough. It would be rough. We'd have to do string equal generator expression on our compiler. In that case, just wrap it with if and if. That's what I usually do. Like that. I think we could just have a generator expression and have each one of these only added, or like you said, we could probably just do this. I can do that if that's the problem. Yeah, this is just something that needs to be fixed before the merge, because we can't include -Ws, because MSVC uses something like this type of syntax. So trying to do what we need does not work, sadly. So it says, I'd have to figure out generator expressions, how generator expressions work though, lol. Yeah, just don't worry about it if you're really worried. All we have to do is comment it out, right? Or just remove it as from the actual Git repo. Having it on the machine is the best idea. It should be on and it should be by default. It's just that not everybody uses GCC. I just had to add them, especially WError equals return type. That's the most important one. You're correct. We should definitely have a void return as well. Otherwise, it'll compile if you forget a return statement in a function that returns an error. Yeah, I've done it. Oh, I've done it. Yeah, that's not a big deal. You know what we could do? Could add a to-do here, and then just have it mtx webs and values, even though they're unused. It's a mess, but it works. Too many arguments for format. There you go. You figured it out. Lamau. Okay. This is actually very cool. Also, I don't know if you noticed, but we're actually allocating registers properly now, just by changing that to an OR equals. Oh! Look at all this register coalescing we could do, though. R1 equals R1, R1 equals R1, R1 equals R4. It's like, or... Saraid says, nice. I mean, you wrote it. You did all this. All I did was go over the concept for 4 hours until I understood it, right? Oh, that's so good. This is awesome. It's working. This is so pog. Oh, it works. Oh, this is actually beautiful. Yeah, we may actually never need this if we just copy our temporary into R1 and x86-64. I see where you're starting to go now, where we don't need the to address. Sir Aid says, you should be able to continue working on the compiler next stream, it seems. I know! What am I gonna do? I'm gonna have to write code? What am I, a pleb? Sir Aid says, yeah, I know, you can just get rid of the phi. Isn't that beautiful, though? So we're gonna have our virtual language and our like translated hardware non-virtual language, right? Because the hardware is going to have specific references to actual hardware registers. So I feel like we should separate these two syntaxes very distinctly. That's going to be so cool. I am so excited. By the way, Sir Aid, thank you for making me learn this. I didn't want to. But I have, and I am now glad that I have. But at the beginning, if you asked me, I would say, hell no, I don't want to spend 2 days learning something that really doesn't change the output at all. But that's such an incorrect view on things. My perspective so often is built from results. It's like, oh, what does this result in? If this doesn't do anything, who cares? but like laughing doesn't do anything, but you should probably still do it. You know what I mean? So my brain is a little too strict in that regard, I think. So I'm going to try and be more open in the future. And if you feel or hear me doing it again, say, hey, you're doing your thing again. Keep an open mind, buddy. You know what I mean? Be sure to remind me, like, hey, you're being an idiot. Remember last time when you said everything was fine and all you just made this big deal out of nothing? It's like that. Stop doing it, right? Let me know if I'm being an asshole, is basically all I'm saying. Sir Aid says also, for compile time evaluation, you can just evaluate the IR. Oh, you don't even know the plans I have for compile time evaluation, buddy. You don't even know. No, you do know. But you're correct. We can actually just build an actual interpreter for this IR, and then basically we can just have that work. Isn't that beautiful? Beautiful, beautiful. What if we could have the standard out of shell commands as a string in the... Oh. So what if you could, like, what I'm saying is you could compile time evaluate a shell command, and the standard out of the shell command, that would actually be a string return value from the shell command. And you could also get, like, the integer return value of the return code. Sir Aid says, ah, yes, let's make Perl, lol. Well, no, but the difference is it's compile time. So the developers will have, you could write tools that create strings for you and create different data, right? Because standard out, you can just print bytes too. So you could have arbitrary data passed between programs at compile time. I don't know why that's helpful, but it just sounds fun. Just how much that would open up. Like, oh my god, the computers are ours. No, I have so many ideas. I also want to make, like, this IR a backend within itself, because I want to write an IR. Basically, I want to write an IR interpreter, like you were saying, for compile time evaluation, but I want it to be its own program so that you can have programs either compiled or interpreted. The only problem is we're going to have to do just-in-time compilation for external calls, which is a whole thing. But I think using libgcc-jit, we could actually create, like, an actual interpreter that makes sense and works. Even though Suraid says external calls are easy. Yeah, interpreters deal with external calls the best. It's easy. You know, you just link the external symbols into your runtime, and then it's like, wait, just do dlopen dlsim on Linux. We can use dynamic linking. Okay, that is an option. And we could just get to the C library and many other libraries that way. That's not a bad idea. We could also use just-in-time compilation and not do any runtime actually linking and have build little executable programs that do the external calls with different command line arguments. Right? We'd basically create, like, a little web of programs. It'd be beautiful. I have so many ideas. And then I also want to make, this is probably cursed, I want to make a backend for Python. I'm just going to let that sink in. I want to convert this IR into Python. Again, external calls, big problem. Definitely going to have to use dlopen or dlsim in Python. Sir Aid says, I mean, I was going to make a JavaScript backend, so this is going to be the best. The one, a compiled language that only compiles to interpreted languages. I don't know why I find that so funny. Oh, we got a raid. What's going on? First time chat from a new viewer. Sit Leto, first time chat from new viewer. Kazanis, what is up? Kazanis is raiding with a party of 4. Thank you so much, Kazanis, for the raid. Welcome, everybody. How's it going? We're ending our stream now, but guess what? We actually, we did our thing. We, also, Sitleto, thank you so much for the follow. Kazanis says, yee, good. It's so good to hear, Kazanis. Thank you for the raid. We were writing some Python. Nice. We were just talking about Python. We were talking about how our intermediate representation of our compiled language. This is a compiler, by the way. Everybody that just showed up, Kazanis, shout out for the follow. Sitleto, shout out for the follow. Thank you so much. We were just talking about Python. We are writing a compiler that compiles this language right here. Right here. Let me load my editor thing. And effectively, this language gets compiled into this intermediate representation. Kazanis says, yeah, I picked you for the raid because of you developing something interesting. Hey, compiler is interesting enough. That's right, that's right. We love compilers around here. Anyway, this code, this source code of a language I made up, on the left gets converted, or at least the main function. We're not looking at any of this. Don't worry about that. But the main function, which is this reassignment of this variable, this function variable to a lambda. We have this integer variable assigned to 16/4, and then we have the greatest common denominator Euclid algorithm used to get the greatest common denominator of 88 and 32. This is just a test program, but as you can see, R8 is a global address of function 0. So this lambda gets generated somewhere in the code, and we load its address into this temporary R8. This temporary R8 is stored in the global variable GCD Euclid, which is this assignment here. So this lambda generates a temporary, which loads an address of a function. Then we store the function address in our variable, because we have first-class functions. Kazanis says, I would like to create my own language, but I am not good enough at this type of programming yet. If I believe you are. Don't put yourself down, Kazanis. Kazanis says, if you got any good resources, feel free to send them my way. Kazanis says, yeah, working with registers, I see. These are not registers. These are temporary values in our intermediate representation. That's a little bit complicated. Basically, these are registers. They're just virtual registers. They never exist in any hardware implementation. What we actually do is we figure out, okay, all of these temporaries, some of them can be stored in the same registers. So for example, R16, R15, and R1, 15, 16, and 1 can all be stored in the same register, so they get into the same web. Kazanis says, I mean, I worked more with data processing and stats, etc. Sitleto says, before every var or def, you're going to have to type kazanis.kapow.function. Lamau. Sitleto, that's hilarious. Sitleto says, I don't know what is happening on your screen, but it looks fire. Lamau. Basically, we just solved this huge register allocation problem. So before, these are virtual registers, and we need to somehow map them to hardware registers. So first thing we do is collect virtual registers that can just be implemented as one hardware register. And these are called webs. So each of these webs needs a hardware register, right? But some of these webs may be able to use the same hardware register. Does that make any sense? So while these temporaries must be stored in the same register, these webs may also be stored in the same register, but they don't have to be. Kazanis says, how will you translate this to different CPU architectures? We are already doing that, actually, with our backend. So if you take a look in the GitHub link, you can check it out there. But you're going to have to go to Sir Aid's fork, because this is not merged. It's actually still part of a work in progress. If we go to our code gen, you can see in this folder, I actually have the IR get generated. Sir Aid wrote all this. Thank you so much. And register allocation. But then we have an x86-64 backend. And in this backend, you can see that all we effectively do, it's kind of complicated. Don't worry about it. Effectively, all we do, where are we at? F emit, blah, blah, blah. Yes, instruction. So it's commented out right now because it wasn't working. We're getting it working because this is a huge refactor of our entire code generation backend. In any case, what's going to happen is when we load an immediate value, for example, when we have immediate 4, then we'll call CodeGen load immediate. CodeGen load immediate will delegate to the different backends based on some compiler flags. And then if it's x86-64, it'll call this backend, in which case we will emit an immediate to register move instruction with the immediate and the result as variables, as operands. Kazanis says, too complex for me. Before you write it off as too complex, I do want to show you something I've been working on. Is that okay? Because I have been working on a file called developers.tech. And if you don't know about LaTeX, it's a markup language, much like HTML, but it's more powerful. It's not more powerful, but it's more powerful in less code. And it's meant to write PDFs. So if we compile this tech file into a PDF, and this tech file you can find in the GitHub repo, so you can actually compile this PDF for yourself. Kastanis says, I write in LaTeX all day, every day because I write scientific articles. Perfect. So you're going to understand this perfectly. I wrote an entire paper on the internals, a developer's manual of the compiler. Also, there's not a name yet. This is just a placeholder for the language name. Effectively, this goes over all of the pieces of the compiler, why they are the way that they are, how they are the way that they are, and what they are, right? So you can see that this parsing example, we have some code that looks like the code you saw before. And then this gets generated into an AST, which is a program, a variable declaration, blah, blah, blah. And this completely represents the program. And this actually gets stored as a data structure called a node or an AST. And this abstract syntax tree basically, Kazanis says, want to have a look at the work I dabble in daily on ResearchGate? Absolutely, I want to check it out. Kazanis, thanks for showing up. Thank you for the raid. It's so interesting to talk to new people. We go over type checking. It's not complicated. Code generation is where things get complicated. Before, we would just generate code directly from an AST. So this program AST, we would just iterate over every node and all of its children, and then we would generate code for it. A declaration of an input condition would allocate stack space. A declaration of an if condition would allocate stack space, allocate stack space, allocate stack space. An assignment, we'd basically go through and say, okay, on the right-hand side, move this value into a register. Or if it's an expression, move its result into some register, right? However, while that did work, it was very inefficient, and it made it very difficult to actually move further past some basic programming language features. And it also makes optimizations literally impossible. How would you optimize this AST? No clue, right? Not a single idea. Hey, Kazanis with the link. Let's check it out. Connect with experts in your field. Join for free. No. How do I read this? Publications? Ooh. I'm very interested. I'm very interested. Download full text PDF. Beautiful. Is there, can I read it online? Read full text? There it is. Nice. I'm actually interested in this. Were they color red or color blue? So based on where they are, number of countries represented. This is awesome, by the way. Wonderful little article. I want to read it actually in more detail. Oh, this is cool. So you go over the time. Oh. Interesting. It's sideways. Just turn your head, it'll be fine. This is really cool. You do stuff like this every day? I'm kind of jealous. I wish I could do stuff this complicated and keep track of it. I've done this one, and it's been a big job. Using a classifier for detecting winners, losers. So you're trying to figure out, does game time depend on one person winning or the other? Does how many players there are. Does what country they're from matter? So you're trying to figure out the determinants, the variables. Casanas says nah. I very often get things completely wrong, so feel free to let me know. Casanas says, I mean, yeah. What? Basically, you're trying to figure out, but more the in-game variables. Okay, so like the literal in-game changes. Oop, I just zoomed and everything broke. Okay, yeah, so like minerals used. Oh, so this paper would basically let you say, if we use less minerals, we'll win more times. But that's incorrect, based on what I'm looking at. No, that's just the minimum. So the average, that's true. So if you used more minerals, the average in the winning team was higher than in the losing team. Kasana says, yeah, more spending and better spending. Collection rate. So obviously you're more likely to win if your collection rate is higher. Ooh. I mean, these are technically within the margin of error, so it's hard to tell. But again, everything wondering what makes people win or lose is going to be within the margin of error. So what are you going to do about that? This is very cool. I'm actually, ooh, a train is coming through our PDF. Oh no. What happened? Emacs, why? Lamau. But then you get the results and classification. Nice. Receiver operating characteristic curve. I don't know what that is. I'm not smart enough to know what this is. Key findings. There's a lot of findings. Is there a conclusion? Yeah. It is possible. Nice. So you can actually use a computer to determine who's going to win. Or more likely to win, is what I should say. Very cool. And then just definitions. Very cool. Thank you so much for sharing this. I love learning more. And it's just awesome. Thank you so much. Let's get this train out of here. But yeah, I wrote an entire LaTeX paper on how our compiler works and why this intermediate representation is even needed. I am going to rewrite this. This was written on stream as part of me learning, not all of it, but most of it was written on stream as part of me learning intermediate representation, why it's even needed. Kastanis says, is this in the repo? Yes, this is in the repo. It is called developers.tech. And it is, we can probably push it, because I'm sure I made some changes. Yeah, why not? Yep, everything should be good. We'll push these, because I don't think the IR branch has affected anything in the docs folder, so we should have no merge conflicts, and this will just be docs update developers.tech. Perfect. We also touched reference.tech, but it's not important. We just moved chapter names upwards. Hey. So with that, yeah, this is now in the GitHub, the up-to-date version. It's not perfect, and not everything within it is going to be correct, because I just wrote it and I learned this today. So bear with me, right? I'm not an expert. I just look like one. Effectively, for register allocation, we build webs, which is a list of temporaries, which are these R0, R1, R2, R3. These are all temporaries in our intermediate language, which I should probably make more obvious. But with these temporaries, we can then say, if they must be stored in the same hardware register, plop them in the web together. So this doesn't intuitively make a ton of sense. Why do we need to build webs if we already have values? And again, this is a work in progress. We are moving away in the code base from ever using webs. But currently, webs are used, so this is how it works. Currently. you collect all of the webs, which is a list of temporaries that must be stored in the same hardware register. And basically all of our temporaries, they must be stored. They can't be stored in the same register. Actually, that's incorrect. It's not that they can't be, it's that none of them must be stored in the same register. I know that's kind of confusing, but basically R0 may be stored in the same place as R1, but R0 and R1 won't always be stored in the same place. And there are situations in which that does occur, like in our actual implementations. When we get to, where are we at? Like code.s. Why? See, when we get to our actual implementation, you can see that some webs contain multiple values because they are copies of other temporaries, like R1 being a copy of R16, R16 being a merge of R15, right? So the idea is that these temporaries, all of these can be stored in one web. And in doing so, that means that these must share the same register. So during register allocation, right? Attempting to delete main window of frame. Why is this not a main, why is this a side window? Oh, it's because I'm in the, yeah, there we go. Gotta love Emacs. Hostman says, why not Graph? Because I'm not writing a man page? No, I don't know. I just don't know Graph. I know more LaTeX. So after we build these webs from this excerpt example, right? Then we can say, okay, each of these webs needs a register. Some of them may have the same register, so how do we actually interpret this? And I don't have this written out in the file yet, but I do have it written out in this terrible Blender file that we went through today. So effectively, this is an example of a real world, our compilation, right? So this is an example of our webs. Here's a bunch of webs, and they're organized in a graph G, right? So each web, web 1, web 2, web 3, etc., they're organized in this graph. And the idea is if they interfere, which means that they cannot be stored in the same register, which has to do with lifetimes of variables. So if this temporary lives at the same time as another temporary, and these temporaries are in separate webs and you're comparing them, then they must interfere because these temporaries interfere. And all that means is that they can't go in the same hardware register. So R0 lives through A, B, and C, right? R1 lives through B and C, and because R0 and R1 are in W0 and W1, this means that web 0 interferes with web 1, meaning that they are connected with an edge in our graph. So each one of these, active layer not shown, okay. Each one of these, right? Each one of these edges, this one, this one, this one, all of them, these are all an interference, which means that these two webs cannot be stored in the same register. This is getting into the weeds of it, right? If anyone is still here from the raid, you're a legend if you stuck around through this. This is literally graph theory. So with each interference represented as an edge in our graph, and with each web represented as a vertex or a node, there is an algorithm that we can use. Whoops, went 3D. There's an algorithm we can use to actually color this graph. Why is that important? Because colors can correspond to a register, a hardware register, and if you color an entire graph, then that means each color can be corresponded to a register, and then each web has been allocated a hardware register, and then anytime you access a temporary from within that web, you just use that register that's been allocated. And effectively how this works is you choose some number k, and this is your maximum number of colors. So k is equal to your number of colors that you're going to color this graph with, right? And once you have your number of colors, that means that you can start to do comparisons and say, pick any node within the graph. In this case, we pick W1 first. And when you pick W1, it has a degree, which is what this refers to, W1 degree, right? That's how that would be written. And the degree of a vertex within a graph, I don't know if you know this, a degree of a vertex within a graph or a node is actually just the amount of neighbors. So for example, W1, it's kind of all covered up. We won't look at it. W5, you can see that it has W8 as a neighbor, W4 as a neighbor, and W7 as a neighbor. So that is 1, 2, 3 neighbors, which means the degree of W5 is equal to 3. Is that making sense? With this degree, if it's less than k, there's a rule you can apply where you just remove the entire node from the graph. Gone. That's why all these x's are here. So you can see W1 has been x'd out, W1's connections, all its edges, have been x'd out. And imagine that W2 and W3 haven't had that happen yet. Effectively, that gets us to a simpler graph, where the degree of all of the nodes in the graph connected to W1 has lowered, which means that because it's less than k, the nodes that we lowered will also hopefully be less than k. Then you just keep doing this. You pick W2, and you're like, okay, what about 2? The degree of it, well, it's now only 2. It's connected to W7 and W3, because after getting rid of W1, it's no longer connected like that. So now it has a degree of 2. 2 is less than k, which we just arbitrarily picked as 10 colors, which means we remove and we push it. We didn't talk about this, but every time you remove a node, you push it onto some stack, and that means that it is colorable. So this stack just contains webs that are colorable. And effectively, you end up with a stack, hopefully with all of your webs within it, and then all you have to do, right, is go through your stack, and each one is connected to other webs, right? So all you do is go through and say, okay, for W1, and here we can look at the actual code now. So for our adjacency lists, these right here are adjacency lists. So W1 can be said to be, adjacent to W2, W3, and W7 because it is connected to them through an edge. So all of the adjacencies of W1 are just the nodes it's actually connected to. And all you do is say, create some list of registers. We use a bit mask. Create some bit mask and set it to 0 entirely. For every interference, for every adjacency, every node it is connected to, go through and set or the mask, right? So when we actually assign registers, min register. So here, we go through all of our interferences in our interference list, which is this list right here from W1. So we're trying to get a register for W1, let's say. And we say, okay, for every interference in the list, add to the bit mask the register that's been assigned to the interference. Well, this is 0, 0, and 0, because we haven't actually colored any of these nodes yet. They're not colored. So what this means is that our bit mask is 0. Then we find the first not set bit, because this means not, right? So we find the first bit that is not set within this bit mask, which happens to be this bad boy right on the end. That's the first not set, so we return bit index 1. And then we color W1 with bit index 1. So after we get this color from min register, we get a register, which is our colors, right? Then we set the color of our node to register. So W1 is now colored with 1. So now when we go to W2 and apply this same little technique, in W2, we end up with W1 here, and W1 here will actually have a color that isn't 0, and because it's not 0, then the bit mask that it pointed to, this bit right here, will be set by these for loops, going over the interferences, because W1 is an interference. Then it won't be stored where W1 is stored. It'll be stored next to it, somewhere else. So we assign 2 to W2. So now W2 has been colored. W1 has been colored. W3 has W1 and W2, as you can see. So both of those, also I just said both, kill me. Both of those will be set in the bit mask, and then you return the next one, index 3. So now W3 will get index 3, right? So it gets colored with the number 3, let's say, which could also be like red, green, blue. It doesn't matter. Coloring is a mathematical term, not an actual color. W4 interferes with webs 5, 7, and 8. I stopped writing W's because I was tired. So W4 goes to 5, 7, and 8, which makes sense, goes to 5, 8, and 7. Those have not been colored yet, so we get another 0 case, which means guess what? The mask is 0, and we return index 1. So what we've just effectively understood is W1 and W4, these two webs, web 1 and web 4, these can share a hardware register. Share register. Oh God. I'm writing with a mouse. Please forgive me. Oh God. Oh God. Okay. Share a register. Look at that. And because we did all this complicated math, it means that it doesn't matter, right? These can share a register and they'll never screw with each other's value. So you can assign both of these to 1, and then you can assign 1 to, example, a register racks. So now every value that is colored with the number 1 actually just gets stored in racks. And that is called Chaitin-Briggs register allocation. Welcome to science. No, I'm just kidding. Basically, it's just a really complicated algorithm to figure out whether all of our intermediate representations, temporaries, can be stored in the same or not the same hardware register, because these are virtual registers. So actually storing in hardware registers looks like this. So you can see we move from our temporaries, which are all different, R8, R9, R10, R11, R12, R13, R14, R15, R16. These change and get mapped to actual hardware registers, which we're still working on the syntax. So R2 is a hardware register, so this is a colored with 2, right? Is that starting to make sense? Colored with 3, colored with 2. And you can see we actually start to reuse the same registers for different instructions. R2 is used here, 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 and here. And what this does is effectively undoes our static single assignment conversion. Whereas before, R8 was only ever assigned to once and lived until it died, its last use in the program, just these little here. Now, R2 represents R8 in this part of the program, but in this part of the program, it now represents R9, and it lives until R9 does. Is this starting to make any sense? Basically, we've mapped from our temporary registers into our hardware, very non-temporary registers, right? So all of our temporaries have been mapped to a hardware register, and they can now be stored in the proper way. And there's also a lot of stuff that no longer needs to happen. For example, R1 equals phi of R1. This is just R1. And R1 equals copy R1 is, guess what? Just R1. So none of this needs to happen. Sir Aid says, I think what you're saying makes sense, but it's a lot to explain. Yeah, I just went through all of it. It entirely made sense. I may have screwed up a part here or there, but it did make sense, because I actually understand it now. Sir Aid has made this pull request, by the way. He's in chat right now. He's a beautiful legend. It took me 30 minutes to explain that, so yeah, it makes sense. King Bun says, wahoo, still alive. King Buns, thank you so much for sticking around through that. I knew that everyone would get scared away from the raid. I'm like, there's no chance anybody's sticking around, because this is the most complicated thing I've ever described in my life. And people's eyes glaze over very fast. But what I just did, that little 30-minute rundown, That's probably gonna be, oh, first time chat from a viewer. WazUXD says, actually, I'm still here, XD. That's so good to hear. We still have one. WazUXD, by the way, you are a very powerful Twitch viewer, because nobody else is here, I almost guarantee it. That was such a lengthy explanation for stuff that you aren't even probably interested in, right? It's like you haven't even heard of this stuff before, and I just took 30 minutes to explain it. But it's a lot of fun. I love graph theory. Graph theory is fun. I love little graphs. Figuring out how this graph, subgraph, is semantically different from this subgraph. Oh, I love it. I love graph theory. But that's amazing to hear, WazUXD. That's impressive. WazUXD says, I'm dev, so I kinda get it. Nice. King Bun says, it's a lot of fun. I love graph theory, in quotes. It's true, though. It's actually something I enjoy a lot. Figuring out, like, reasoning about all this stuff. Because now I understand it. And it actually makes sense. Isn't that scary? That's the scary part. I actually understand it and it makes sense. Whack. Lamau. King Buns, I'm glad you're still here. I hope you had a great time at your work call, but sadly, we are at the very end of our wits currently, which means also I have to eat lunch. I'm super late to some people. I said I was going to be there earlier, and I am not there earlier. Story Aid says, I'm currently replacing a lot of for loops with vector for each, lol. Ooh, that's awesome. King Bun says, oh, I am surprised you are still live. It's true. We just kept going, baby. I actually fixed the register allocation, too. King Bun's, or not King Bun, Sir Aid had a and equals here instead of or equals, which I noticed, and then I was like, wait a minute. We noticed it at the same time, truthfully. But we figured out, hey, wait a minute. Oh, why work? What happened to code.s? There we go. That's all you changed, right? It really was that easy? Yep, that's literally all I changed. We can check out Git. I changed an empty line in CMake lists. I added an example of division. And then I went to or equals. I also uncommented all the printing, but that's all this is. I just commented out the comments. Legendary. But yeah, so basically, other than changing the printing code, this is literally all I changed, and it works perfectly. It looks beautiful, by the way. Like, this is actually going to generate code that works. This is so satisfying. Oh, yes. WazXD says, it is super cool, but I guess I will stick to, I guess stuff is allocated somewhere in memory. I mean, we're still doing the same thing. Our intermediate representation has no clue where things are stored, which is actually a positive thing. WazXD, if you are interested in where memory is allocated, be sure to check out like my OS. I have an entire OS which goes into much detail about how memory is allocated on a low level. It's in Lenser OS. But yeah, this is on my GitHub, and you can check out, there's many a thing. WazXD says, what? Here. That's yours. Yeah, it's a free and open source OS, but you can actually check out in the kernel how memory is dealt with, mainly in the pre-kernel. You're gonna have to read some assembly, but I hope you're okay with that. Right? So basically, we have to set up the page tables, the virtual page tables for x86-64 from assembly. Otherwise, we have issues with the C calling convention and not being mapped because, yeah. Sitleto says, I just got into your YouTube channel. 6-hour videos of you programming. Do you work at some tech lead or something? King Bun says, no, he's just a crackhead looking for a rock. Crazy what they will do, am I right? Oh, King Buns has it exactly correct. But yeah, this goes over basically the initial bootstrapping of virtual memory from an EFI base. And then from there, we get into K stage 1, where we actually start to set up the first thing we do. Where are we at? This function is monstrous, right? But here's what it does. Basically, we set up the GDT, doesn't matter, interrupts. Then we say memory, init physical, init virtual, init heap, and that is where your memory is stored. If you follow these into the memory module, where is it? Memory. Once you end up here, then there's a physical memory manager, a virtual memory manager, there's a heap, right? And then you can figure out, oh, this is how memory is implemented. This is where it is stored, right? Because this chooses, for example, the physical memory manager. You can free, that just gives you the amount of free RAM, but you can lock pages or free pages. So basically each page of memory is like some chunk. So each chunk of memory can either be locked, which means it's in use, or freed, which means it's not in use. And we use a very simple bitmap for that. But yeah, so if you're very interested in memory, check out the OS. There's lots of memory details. You can check out how the heap is implemented, why you actually get problems when you free something and then continue to use it on the heap. And then you can look at the actual programs that are run by K-Stage 1, because K-Stage 1 actually runs some user space programs. King Bun says, so I'm guessing LenserOS to be compatible with the Fun compiler. LenserOS has its own version of the GCC toolchain. We use GCC 12.1.0 at this point, or 11.2, it really doesn't matter. But yeah, so this is our toolchain. We use GCC, so the fact that we output x86-64 assembly means that GCC can understand it. How beautiful. But King Buns, you're correct. The compiler compiles programs that can run on LenserOS, and it can also run on LenserOS once we get our standard library more up and running. But it turns out writing a libc entirely by yourself is hard. Did you know that? I didn't know that, but it is. And it requires a lot of bootstrapping, because the libc technically has to be present when you compile the toolchain, but the toolchain has to compile the libc. Ooh, who could imagine that a standard library was a pain? King Buns, Lamau, right? Who could imagine? Who would have known? I thought it'd be easy. But no, you can test, like, we have main.c, which actually can write to the standard out file, and you can actually read it in the output of the OS, and that is all that matters. It took me so long to get to here. It's like, oh, that's all that matters. I just want to write to standard out. King Bun says, I think that would be the evil LLVM. Lamau. WazzyXD says, so LenserOS is responsible for intermediate language? No, actually. LenserOS is the reason why we didn't have an intermediate representation. It's on x86-64. Right? Also, I should be looking at Codeberg, but it doesn't matter. It's an operating system for x86-64, very specifically. It's not a cross-platform operating system. So it eventually may be, but right now, very specifically x86-64, which is supported by our, it was the first thing I supported in the compiler. LenserOS actually is going to be a lot like Unix, just with, or it's at least going to have a Unix compatibility layer. I haven't decided, because I want to do POSIX, but I also don't want to do POSIX, because POSIX threads, no. In any case, we've actually done it. This is the end of today's stream, and thank you so much for coming out. We did so much today. Also, King Buns earlier said, He's gonna watch that 30-minute explanation in the VOD. That's a good idea. I went through like speed, like here's how register allocation works. Also, it bothers me that this is to the right. Ah. WazzyXD, shout out for the follow. What's up, WazzyXD? Thank you for following. Thank you for tuning in. Arusia says every OS gotta have that Unix compatibility layer. You're not wrong. Lamau. In any case, thank you everybody so much for watching. If you have any questions, check out the Discord down below, where you can get notifications every time I go live, as well as just general discourse. And see, there was a pull request to Lenser OS that is already merged. Ooh. How about that? How about that? But yeah, I recommend it a lot. Join the Discord, join the YouTube, do the thing, hit the button. Bye-bye, everybody. I love you. I'll see you next time. Bye, Mom. Bye, Dad. Love you.